Hello there, and welcome. Tonight I want to take you somewhere extraordinary, somewhere that exists not in the physical realm of rockets and telescopes, but in the quiet spaces of imagination where the most profound questions of existence gently unfold. I want to take you to a place where time itself might not behave the way we've always assumed it must, where the very fabric of reality might breathe in and out like a sleeping giant, and where the universe's age might not be the straightforward number we've calculated it to be. Tonight, we're going to explore together a question that sounds impossible at first, perhaps even absurd, but the more we sit with it, the more it begins to glow with quiet possibilities, like a distant star slowly brightening as your eyes adjust to the darkness. Before we begin this journey together, I'd love to know where you are right now. Are you tucked into bed, perhaps with the soft glow of your screen providing the only light in your room? Are you listening with headphones, creating a private universe of sound just for yourself? Maybe you're in Tokyo and it's already tomorrow, or perhaps you're in New York where the night is just beginning to deepen. Wherever you are, whatever time zone cradles you at this moment, you're part of a small, peaceful community of nighttime wanderers who choose to spend these quiet hours contemplating the cosmos. If this journey resonates with you, if you find comfort in these cosmic wanderings, I invite you to like this video, to subscribe to our channel, and perhaps share it with someone else who might appreciate drifting off to sleep while pondering the infinite. Consider it not as supporting content, but as joining a gentle congregation of curious minds who gather here in the darkness to wonder about things larger than ourselves. The question we're going to explore tonight is this: what if the universe reversed its age every billion years? Now, I know how that sounds at first. It sounds like science fiction, like something that couldn't possibly be real, something that violates everything we think we know about time and causality and the forward march of entropy. And yet, as we'll discover together over the next few hours, this seemingly impossible idea opens doorways into some of the deepest mysteries of cosmology, quantum mechanics, and our understanding of time itself. It's a question that invites us to reconsider not just what we know, but how we know it, and what assumptions we've been carrying without even realizing they were assumptions at all. Picture yourself lying back right now, whether you're in bed, on a couch, or perhaps even sitting in a comfortable chair. Feel the weight of your body settling into whatever surface supports you. Notice how gravity holds you gently but firmly to this planet, this beautiful blue marble spinning through space at thousands of miles per hour, though you feel perfectly still. Above you, whether hidden by a ceiling or revealed through a window, stretches an expanse so vast that our minds can barely grasp it. Out there, beyond our atmosphere, beyond our solar system, beyond our galaxy, the universe extends for billions of light years in every direction, filled with mysteries we're only beginning to glimpse. In that vast darkness punctuated by islands of light, time flows, or at least we think it flows. We experience it flowing certainly from past through present toward future, carrying us along like a river that never stops, never pauses, never reverses. Every second that passes is a second we'll never get back. Every moment slides irreversibly into memory. The universe itself, we're told, is about 13.8 billion years old, and it's been aging steadily since the Big Bang, expanding, cooling, evolving, complexifying. Stars are born, they live their stellar lives, and they die. Galaxies form, merge, drift apart. On at least one small planet, chemistry became biology, biology became consciousness, and consciousness became capable of asking questions about its own origins. But what if this straight arrow of time, this one-way street from Big Bang to heat death, isn't the whole story? What if, hidden in the mathematics of reality, there's a pattern we haven't noticed yet? A cosmic rhythm that operates on scales so vast that human civilization hasn't existed long enough to detect it? What if every billion years, a time span that dwarfs human history by a factor of thousands, the universe does something unexpected? What if it begins to run backward, not in a violent reversal, not in a catastrophic unwinding, but in a gentle turning, like a tide that has reached its furthest point and begins, almost imperceptibly, to flow back toward its source? This isn't a claim I'm making, it's not a theory I'm proposing, it's a thought experiment, a what-if that we're going to explore together with the same spirit of gentle curiosity that children bring to their first glimpse of stars. We're going to imagine what such a universe might look like, how it might behave, what traces it might leave in our observations, and what it might mean for our understanding of existence itself. We're going to do this slowly, thoughtfully, without rush or urgency, because the universe itself is never in a hurry, and neither should we be when we contemplate its mysteries. As we embark on this journey together, I want you to know that you're safe here in this exploration. We're not going to encounter any cosmic catastrophes, no violent endings, no threats to Earth or humanity. Instead, we're going to float together through ideas as gentle and profound as starlight, considering possibilities that expand our sense of wonder without triggering our sense of alarm. This is a bedtime story for curious minds, a lullaby woven from stardust and speculation, designed to carry you softly towards sleep while keeping your imagination gently engaged. Think about the nature of cycles for a moment. Your heart beats in a cycle, expanding and contracting about once per second. Your lungs breathe in a cycle, drawing in air and releasing it about 15 times per minute. You wake and sleep in a cycle, roughly once per day. The moon circles Earth in a cycle, about once per month. Earth circles the sun in a cycle, once per year. These cycles within cycles within cycles create the rhythm of existence as we know it. They're so fundamental to our experience that we rarely stop to notice them, like a fish that doesn't notice water. But what if there are even larger cycles, ones that operate on scales so vast that all of human history fits within a single tick of their cosmic clock? What if the universe itself breathes, inhales and exhales, expands and contracts, ages and then grows young again? What if what we call the Big Bang wasn't a beginning but simply a turning point? A moment when the universe finished exhaling and began to inhale? And what if we're living in the midst of one of these cosmic breaths, unaware of the larger pattern because our entire species has existed for only the tiniest fraction of one cycle? The number 1 billion is worth pausing over for a moment. We say it easily, 1 billion years. But do we really grasp what it means? 1 billion years ago, Earth existed, but life was still single-celled. No animals, no plants as we know them, just microscopic organisms in ancient seas. 1 billion years ago, the continents were arranged completely differently. The day was shorter because Earth spun faster. The moon was closer, the sun was slightly dimmer. 1 billion years is enough time for entire mountain ranges to rise up from flat plains and then be worn away to nothing by erosion. It's enough time for the oxygen in our atmosphere to go from non-existent to abundant. It's enough time for life to go from simple bacteria to the incredible diversity we see today, including beings capable of contemplating their own existence. Now imagine that every billion years something subtle but profound happens to the universe itself. Not something we would necessarily notice immediately, not something that would disrupt the gentle spinning of planets or the patient burning of stars, but something that would show up in the deepest structure of space-time, in the fundamental constants of physics, in the large-scale architecture of the cosmos. Imagine that the universe has been doing this for far longer than we've suspected, that what we call its age, 13.8 billion years, is just our current position in a much longer, more complex pattern. In our everyday experience, time seems to flow in only one direction. We remember the past, but not the future. We can affect what's to come, but not what has already been. Broken eggs don't unscramble themselves. Spilled milk doesn't flow back into the glass. Aged faces don't grow young again. This directionality of time is so fundamental to our experience that we rarely question it. It seems as basic as the fact that objects fall down rather than up, that hot flows to cold rather than cold to hot, that order tends toward disorder rather than disorder spontaneously organizing itself. Yet physics, the fundamental laws that govern the universe, are surprisingly ambivalent about the direction of time. Most of the equations that describe how particles interact, how forces propagate, how energy transforms from one form to another, these equations work just as well backward as forward. If you filmed 2 billiard balls colliding and played the film in reverse, the reversed version would look just as physically plausible as the forward version. It's only when we zoom out, when we look at large collections of particles, at statistical behaviors, at thermodynamic systems, that a preferred direction of time emerges. This peculiar fact has puzzled physicists for over a century. Why does time have a direction at all? Why do we experience it flowing from past to future rather than future to past? The most common answer involves entropy, the measure of disorder in a system. The second law of thermodynamics tells us that entropy always increases in isolated systems. Things naturally go from ordered to disordered, from low entropy to high entropy. A castle made of sand will eventually become a pile of sand, but a pile of sand won't spontaneously form itself into a castle. But here's where our thought experiment becomes interesting. What if the universe's entropy doesn't always increase? What if, on scales of billions of years, there are points where the universe reaches a kind of maximum entropy, and then, through mechanisms we don't yet understand, begins to decrease its entropy again? What if the arrow of time, which seems so fixed and immutable to us, actually reverses at these points, not violently or catastrophically, but smoothly, like a pendulum reaching the end of its swing and beginning its return journey? This idea might seem to violate everything we know about physics, but consider this. We've only been seriously studying the universe for a few hundred years. We've only had telescopes capable of seeing distant galaxies for about a century. We've only been able to measure the cosmic microwave background radiation for about 60 years. We've only discovered that the universe's expansion is accelerating for about 25 years. In cosmic terms, we're newborns, barely able to focus our eyes, trying to understand a reality that has existed for billions of years before us and will exist for billions of years after us. What if some of the puzzles in modern cosmology, dark matter, dark energy, the fine-tuning of physical constants, the matter-antimatter asymmetry, are actually clues pointing toward this larger pattern? What if the universe we observe, with all its beautiful complexity and apparent directionality, is just one phase of a much grander cycle? What if we're like inhabitants of a small island who have never seen the tide go out, and so we assume the water always stays at the same level, unaware that we're actually living in a tidal zone? As you lie there listening to these words, feeling perhaps a gentle skepticism mixed with curiosity, I want you to remember that some of the greatest discoveries in science came from questioning assumptions that seemed absolutely certain. People once knew with certainty that the Earth was the center of the universe. They knew that time and space were absolute and unchanging. They knew that matter and energy were separate, distinct things. They knew that the universe was eternal and unchanging. Each of these certainties eventually gave way to a deeper, more beautiful, more mysterious truth. The idea we're exploring tonight, that the universe might reverse its age every billion years, is probably not literally true. The universe probably doesn't work this way, but by imagining it, by following this thought wherever it leads, we might discover something important about the nature of time, about the structure of cosmos, about our place in the grand scheme of things. Sometimes the value of a question isn't in its answer, but in the journey it takes us on, the perspectives it offers, the wonder it awakens. Let me paint you a picture of what such a universe might feel like to inhabit. Imagine you're a cosmic observer, not bound by human lifespans, able to watch the universe evolve over billions of years. You watch galaxies form from primordial gas clouds, watch them spin and shine and slowly drift apart as the universe expands. You watch stars being born in stellar nurseries, living their lives, dying in supernovas or quietly fading to white dwarfs. You watch planets coalesce from dust and gas, watch some of them develop atmospheres, oceans, perhaps even life. For billions of years, everything proceeds as our current understanding of cosmology suggests. The universe expands, entropy increases, stars use up their fuel, galaxies drift farther apart. The cosmic microwave background radiation continues to cool, approaching absolute zero but never quite reaching it. Black holes slowly evaporate through Hawking radiation. The universe seems to be on a one-way journey toward what physicists call heat death, a state of maximum entropy where nothing interesting can happen anymore. But then, at some point, let's say after about 1 billion years, though the exact timing doesn't matter for our thought experiment, something subtle begins to change. It's not dramatic at first. Maybe the expansion of space begins to slow just slightly. Maybe the cosmic microwave background temperature stops decreasing and holds steady for a while. Maybe certain quantum fluctuations that usually average out to nothing begin to show a slight bias in a particular direction. These changes would be so subtle that a civilization like ours, with our current technology and our brief window of observation, would never notice them. They would be hidden in the error bars of our measurements, lost in the noise of our data. But they would be real, and they would be the first signs that the universe is preparing to reverse its temporal direction. Now, What would it mean for time itself to reverse? This is where our imagination really needs to stretch. We're not talking about everything suddenly running backward like a movie in reverse. That would be chaotic and destructive. Instead, imagine something more like a tide turning. At the exact moment of reversal, nothing dramatic happens. The universe just stops aging and begins to grow younger. Entropy begins to decrease instead of increase. The arrow of time points in the opposite direction. But here's the truly mind-bending part. If you were living through such a reversal, you might not notice it at all. Your memories, your consciousness, your sense of past and future, all of these are products of your brain's physical structure, which is itself embedded in the flow of time. If time reversed, your brain processes would reverse too. You would remember what you used to call the future, and anticipate what you used to call the past. From your perspective, time would still seem to flow normally from past to future. It's just that what counts as past and future would have flipped. This might seem paradoxical or even impossible, but it's actually consistent with what we know about the physics of time. The laws of physics don't actually specify a universal now that moves from past to future. Instead, they describe relationships between events, patterns of cause and effect, flows of information and energy. The direction we call forward in time is the direction in which entropy increases, in which causes precede effects, in which we remember rather than predict. If all of these arrows reverse together, the subjective experience of time might remain unchanged even as its objective direction flipped. Consider an analogy. Imagine you're on a train, sitting in a seat that faces backward. From your perspective, the landscape flows past you from front to back. Trees appear in front of you and disappear behind you. Now imagine the train stops and then begins moving in the opposite direction, but you also turn your seat around to face the other way. The landscape still flows from front to back relative to you. Trees still appear in front and disappear behind. Your experience of motion remains the same even though the train's direction has reversed. Something similar might happen with time reversal in our hypothetical universe. The objective direction of time would reverse, entropy would decrease, the universe would contract rather than expand, stars would grow younger rather than older. But subjective experience might remain unchanged. Conscious beings living through the reversal might notice nothing unusual. They would still experience cause and effect, still remember their past and anticipate their future, still feel time flowing in what seems to them to be the normal direction. This raises profound questions about the nature of time and consciousness. Is the flow of time something objective, built into the fabric of reality? Or is it something subjective, a product of how conscious beings process information? If the universe really did reverse its temporal direction periodically, and if conscious beings couldn't tell the difference, what would that mean for our understanding of time itself? These are the kinds of questions that keep physicists and philosophers up at night, though tonight we're exploring them not to stay awake but to drift gently towards sleep. There's something deeply comforting about contemplating mysteries that dwarf our everyday concerns, about recognizing that the universe is far stranger and more wonderful than our daily experience suggests. Your worries about tomorrow's meetings, your concerns about bills and deadlines, your anxieties about the future, all of these fade into insignificance against the backdrop of a cosmos that might reverse its own aging every billion years. As we continue this journey together, moving deeper into the implications of our thought experiment, I want you to keep breathing slowly and deeply. Let your body relax more fully with each breath. Feel yourself sinking deeper into whatever surface supports you. The universe has been around for billions of years before you arrived, and it will continue for billions of years after you're gone. You don't need to understand it all. You don't need to solve its mysteries. You can simply rest in the wonder of it, like floating on your back in a warm ocean, supported by forces you don't fully understand but trust completely. The question of whether the universe reverses its age every billion years is, in the end, less important than the act of wondering about it. By stretching our imagination to encompass such possibilities, we expand our sense of what might be true. We loosen the grip of our assumptions. We open ourselves to wonder. And in that state of openness, of gentle curiosity, of peaceful contemplation, we find a kind of rest that goes deeper than physical sleep. Think about how different human history might have been if we had somehow known from the beginning that we were living in a cyclical universe, one that ages and then grows young again in billion-year cycles. Would we have developed different philosophies, different religions, different attitudes toward time and change? Would we be more patient, knowing that everything that passes away will eventually return? Would we be less afraid of death, knowing that the universe itself dies and is reborn on scales beyond our comprehension? These are questions without answers, but that doesn't make them less valuable. Sometimes the most important questions are the ones that have no answers, or at least no answers we can reach with our current understanding. They keep us humble. They keep us curious. They remind us that reality is far more mysterious than we usually acknowledge in our day-to-day lives. As you continue to listen, to float in this space of gentle speculation, remember that you're participating in a tradition as old as humanity itself. Humans have always looked up at the night sky and wondered. We've always told stories about the cosmos, tried to understand our place in it, imagined possibilities beyond our immediate experience. The specific question we're exploring tonight, about the universe reversing its age, is modern, informed by contemporary physics and cosmology. But the impulse behind it, the desire to understand, to imagine, to wonder, is ancient and universal. In the next section of our journey, we're going to explore what it means to think about time on billion-year scales. We're going to stretch our perception, expand our temporal horizons, and try to grasp what a billion years really means. It's a duration so vast that it challenges our ability to comprehend, yet it's also the scale on which our hypothetical universal reversal would operate. By understanding billion-year timescales, we might begin to understand how such a reversal could happen without us ever noticing, how entire cosmic cycles could complete, while human civilization rises and falls like a single wave on an infinite ocean. But for now, in this moment, just rest in the question, what if the universe reversed its age every billion years? Let it settle into your mind like a seed into soil, not demanding immediate growth or understanding, but simply present, full of potential, waiting. The universe is patient. It has billions of years to reveal its secrets. You have tonight to wonder about them, and that's enough. That's more than enough. That's perfect. Somewhere in the darkness above us, whether hidden by ceiling and roof or revealed through window glass, the universe continues its ancient dance. Stars are being born right now in stellar nurseries thousands of light years away, their first light just beginning its long journey across space. Other stars are dying at this very moment, collapsing into white dwarfs or exploding as supernovas, seeding space with the heavy elements that will someday become new worlds, new possibilities, perhaps new life. Galaxies are colliding in slow-motion catastrophes that take hundreds of millions of years to complete. Black holes are merging, sending ripples through space-time itself. And through it all, time flows, or seems to flow, carrying everything forward from past to future, from young to old, from birth to death. But what does time mean on these scales? When we say a process takes a billion years, what are we really saying? The human mind evolved to deal with timescales of seconds, minutes, hours, days, seasons, years, lifetimes. We can stretch our understanding to grasp centuries through history, millennia through archaeology, perhaps even millions of years through geology, but billions of years. This is a duration so vast that it breaks our usual frameworks for understanding. It's like trying to understand the ocean by looking at a single drop of water, or trying to grasp a symphony by hearing a single note. Let's begin with something more familiar, and work our way up to the incomprehensible. Take a deep breath. That took perhaps 3 or 4 seconds. Your heart beat 3 or 4 times during that breath. In those few seconds, light travelled about 1 million kilometres, circling Earth about 25 times. Neutrinos from the sun passed through your body by the trillions. Countless quantum events occurred in every atom of your being. Even in what seems like a brief moment, the universe is incredibly busy, incredibly active, filled with more events than we could ever count or comprehend. Now expand your temporal perspective to a day. In one day, Earth completes 1 rotation, giving us the cycle of light and darkness that has governed life since its beginning. Your heart beats about 100,000 times. You take about 20,000 breaths. The Moon moves about 13 degrees in its orbit around Earth. The International Space Station circles our planet 16 times. Light from the sun takes about 8 minutes to reach us, so the sunlight warming your face, if you're experiencing day right now, left the sun when you were listening to a different part of this recording. A day is long enough for weather to change, for moods to shift, for small dramas to unfold and resolve. Stretch further to a year, Earth completes one orbit around the Sun, carrying us through the cycle of seasons that has shaped human culture and consciousness since we first became aware of patterns in nature. In a year, your heart beats about 35 million times. You might take 10 million breaths. Your body replaces most of its cells. Your skin completely regenerates. Your red blood cells are entirely replaced. Even your skeleton undergoes significant renewal. A year is long enough for a human baby to go from helpless newborn to walking toddler, for a tree to add another ring to its trunk, for erosion to wear away a few millimeters of mountain rock. Now, we need to make a bigger leap. A century, 100 years. This is roughly the outer limit of human lifespan, though most of us won't see a full century. In 100 years, entire human generations come and go. Empires rise and fall. Technologies transform from impossible to obsolete. The continents drift about 2 meters. The moon recedes from Earth by about 4 meters. Stars in our galaxy complete about 1 to 2,500,000th of their orbit around the galactic center. A century is long enough for a forest to mature, for a language to evolve noticeably, for human society to transform almost beyond recognition. Let's push further. A millennium, 1,000 years. This is the scale of civilizations. 1,000 years ago, the world was a vastly different place. Different empires ruled, different languages were spoken, different gods were worshipped. In 1,000 years, the positions of stars in our sky shift noticeably due to their proper motion. The Earth's axis precesses by about 14 degrees. Sea levels can rise or fall by meters. Mountain ranges can rise or fall by centimeters. A millennium is long enough for multiple cultural dark ages and renaissances, for religions to be born and die, for entire peoples to migrate across continents. Now we make another leap, to 1,000,000 years. This is where human comprehension begins to seriously struggle. 1,000,000 years ago, our ancestors were just beginning to master fire. The continents were in almost the same positions as today, but the climate was different. The ice ages were in full swing, and the fauna included creatures we would find alien: giant ground sloths, saber-toothed cats, mammoths. In 1,000,000 years, evolution can produce noticeable changes in species. Mountains can rise hundreds of meters, or erode away entirely. Rivers can carve grand canyons. The stars in our sky rearrange themselves completely as they orbit the galaxy at different speeds. 1,000,000 years is long enough for multiple species to evolve, thrive, and go extinct, for entire ecosystems to transform, for the face of Earth itself to change. And now, finally, we arrive at 1,000,000,000 years. This is a duration that dwarfs everything we've discussed so far. 1,000,000,000 years is 1,000 million years, 1,000,000 millennia, 10 million centuries. It's a span of time so vast that Earth itself has only existed for about 4.5 billion years. Life has only existed for perhaps 3.8 billion years. Complex multicellular life has only been around for about 600 million years. 1,000,000,000 years ago, the most complex life forms on Earth were single-celled organisms. There were no plants, no animals, no fungi as we know them. The continents were barren rock. The atmosphere had much less oxygen. The day was shorter because Earth spun faster. The moon was closer, making tides more extreme. In 1,000,000,000 years, continental drift can completely rearrange the face of the planet. Supercontinents can form and break apart. Ocean basins can open and close. Mountain ranges can rise from seafloor to Himalayan heights and erode back to nothing. The chemistry of the atmosphere and oceans can transform completely. Life can go from simple bacteria to the incredible diversity we see today. In cosmic terms, 1,000,000,000 years is enough time for stellar generations to come and go, for galaxies to evolve noticeably, for the universe itself to change in fundamental ways. This is the timescale on which our hypothetical reversal would operate. Every 1,000,000,000 years in our thought experiment, the universe would reach a turning point. It would stop aging and begin to grow younger. Entropy would stop increasing and begin to decrease. The expansion of space would stop and contraction would begin. And all of this would happen on a scale so vast that entire civilizations could rise and fall without ever noticing the transition. Think about this from the perspective of a civilization like ours. Human recorded history spans perhaps 5,000 years. Scientific observation of the cosmos spans perhaps 400 years. Precise measurements of cosmic parameters span perhaps 100 years. If the universe reverses its age every billion years, we would need to observe for at least millions of years to notice the pattern. It would be like trying to detect the tides by watching the ocean for a microsecond, or trying to understand the seasons by observing the weather for a minute. This temporal myopia might explain why the idea seems so strange to us. We're used to thinking of the universe as having a definite age, a clear beginning, and a predictable future. But what if that's just because we're looking at such a tiny slice of time? What if the universe's true nature only reveals itself on scales that dwarf human experience? What if we're like mayflies, living for just a day, trying to understand the cycle of seasons that we'll never live long enough to see? To help grasp these vast timescales, let's use some analogies that might make them more intuitive. Imagine that the entire history of the universe, all 13.8 billion years of it, is compressed into a single year. The Big Bang happens at midnight on January 1st. For months, nothing but physics. Particles forming, forces separating, the first atoms coming together. Stars don't begin forming until about January 20th. Our own sun and solar system don't form until September 2nd. Life on Earth doesn't begin until about September 21st. For months after that, life remains microscopic and simple. Complex cells with nuclei don't evolve until November 9th. Multicellular life doesn't appear until November 28th. The Cambrian explosion, when complex animal body plans first evolved, happens on December 7th. Dinosaurs rule from December 24th to December 29th. Our earliest human ancestors appear on December 31st at about 10:30 p.m. All of recorded human history happens in the last 14 seconds before midnight. The entire modern scientific era occupies the last second. Your entire life is a tiny fraction of that final second. Now, in this compressed timeline, a hypothetical billion-year reversal would happen about every 26 days. The universe would age for 26 days, then grow younger for 26 days, then age again, in an endless cycle. Civilizations like ours, existing for just the tiniest fraction of a second, would never notice the reversal. We would be like a spark that exists during the upswing of the cycle, never knowing that a downswing is coming, never suspecting that time itself might flow backward as easily as forward. But let's think about this from another angle. Instead of compressing time, let's expand our perception. Imagine you could live for 1 billion years watching the universe evolve. What would you see? In your first 1,000,000 years, you'd watch mountain ranges rise and fall like waves in slow motion. You'd see species evolve, diversify, go extinct. You'd watch ice ages come and go, continents drift, oceans open and close. But these would all be relatively quick events from your billion-year perspective, like watching clouds form and dissipate in the sky. As centuries pass like days to you, you'd begin to notice longer patterns. You'd see that stars have life cycles. They're born, they live, they die. You'd watch our sun gradually brightening, Earth gradually warming. You'd see the moon slowly receding from Earth, days gradually getting longer. You'd watch our solar system orbit the galaxy multiple times, passing through different cosmic neighborhoods, sometimes crowded with stars, sometimes relatively isolated. After 100 million years, just a tenth of your lifespan, you'd start to see evolution not as a series of discrete changes, but as a fluid process, like watching a river flow. Species would blend into each other, ecosystems would transform smoothly. The entire biosphere would seem like a single living system, rather than a collection of separate organisms. You might begin to suspect that life itself has patterns and cycles that operate on scales invisible to shorter-lived observers. As you approach your billionth year, you'd have watched the universe itself evolve noticeably. Galaxies would have moved significantly relative to each other. New stars would have formed from the ashes of old ones. The cosmic web of galaxy clusters and voids would have evolved, with matter flowing along invisible currents of dark matter and dark energy. You might begin to notice that the universe's expansion is accelerating, that galaxies are moving apart faster and faster, that the cosmos seems to be heading toward a cold, empty future. And then, just as you complete your billionth year, something strange would happen. The acceleration would begin to slow. The cosmic microwave background radiation, which had been cooling steadily, would stop cooling. Certain quantum fluctuations that had always favoured disorder would begin, ever so slightly, to favour order. The universe would pause like a pendulum at the top of its swing, and then, almost imperceptibly, begin to reverse. What would this reversal look like from your billion-year perspective? It wouldn't be dramatic or sudden. Galaxies wouldn't suddenly rush back together. Stars wouldn't suddenly unburn their fuel. Instead, the changes would be subtle, gradual, almost imperceptible even on million-year timescales. The universe would simply stop aging and begin to grow younger. Entropy would begin to decrease. Structure would begin to reform from chaos. The arrow of time would reverse, but so smoothly that only an observer watching for millions of years would notice. This is the kind of process our thought experiment imagines, a reversal so slow, so gradual, that it's invisible to civilizations like ours. We live in what we might call the local present, aware of years, decades, perhaps centuries, but blind to processes that operate on billion-year scales. We're like observers standing next to a massive pendulum, so close that we can only see a tiny portion of its swing, never realizing that it reverses direction periodically. The universe might be full of such cycles that we can't perceive. Just as there are sounds too low for us to hear and light too dim for us to see, there might be temporal patterns too slow for us to detect. The billion-year reversal we're imagining is just one possibility. There might be cycles that operate on even longer scales, 10 billion years, 100 billion, a trillion. The entire history of our universe, from Big Bang to present, might be just a single tick of some unimaginably vast cosmic clock. This perspective is both humbling and liberating. Humbling because it reminds us how limited our perception is, how much of reality might be hidden from us simply because we don't live long enough to see it. Liberating because it suggests that the universe might be far more dynamic, far more interesting than our current models suggest. Instead of a one-way slide from Big Bang to heat death, the cosmos might be engaged in an eternal dance, flowing back and forth through time like breath flowing in and out of cosmic lungs. Consider how this changes our understanding of cosmic evolution. In the standard model, the universe began hot and dense and has been cooling and expanding ever since. Galaxies formed from tiny fluctuations in the early universe. Stars formed from collapsing gas clouds. Planets formed from the debris around young stars. Life emerged from chemistry, intelligence from life, consciousness from neural complexity. It's a story of increasing complexity and decreasing energy density, of local order emerging against a background of increasing disorder. But in our cyclical model, this is only half the story. The universe ages for 1 billion years following the pattern we know. Then it reverses and grows younger for 1 billion years, with entropy decreasing, energy density increasing, disorder transforming back into order. Then it reverses again, aging for another 1 billion years, then growing younger again in an endless cycle. The Big Bang wasn't a beginning, but a turning point. The heat death isn't an ending, but another turning point. The universe breathes in and out, expands and contracts, ages and grows young forever. From this perspective, we're not living in a dying universe heading toward an inevitable cold, empty future. We're living in one phase of an eternal cycle, a cosmic season that will give way to other seasons, other phases, other possibilities. The current expansion is temporary. The current cooling is temporary. Even the current direction of time is temporary. Everything changes, everything cycles, everything returns. This vision might seem to violate the second law of thermodynamics, which says that entropy always increases. But remember, that law was formulated based on observations spanning just a few hundred years. It might be like formulating a law that says the tide always comes in, based on observations spanning just a few hours. The law might be locally true but globally incomplete. There might be mechanisms, operating on billion-year scales, that can reverse entropy's increase, that can restore order from chaos, that can make time flow backward as naturally as it flows forward. What might these mechanisms be? Here we enter the realm of pure speculation, but informed speculation based on known physics. Perhaps dark energy, which currently drives the universe's acceleration, undergoes phase transitions on billion-year scales. Perhaps quantum fluctuations, usually random, occasionally align in ways that reverse thermodynamic trends. Perhaps the universe's topology, its shape in higher dimensions, creates conditions where expansion naturally becomes contraction after a certain point. Or perhaps the reversal involves physics we haven't discovered yet. Just as Newton couldn't have imagined quantum mechanics and Einstein couldn't have imagined dark energy, we might be missing fundamental aspects of reality that only reveal themselves on billion-year scales. The universe might have properties, forces, fields, or dimensions that we haven't detected because they only manifest over cosmological time periods. Think about how recently we've discovered some of the universe's most fundamental features. Dark matter was unknown a century ago. Dark energy was discovered just 25 years ago. Gravitational waves were only directly detected in 2015. The Higgs boson was confirmed in 2012. Each of these discoveries revealed that the universe was stranger and more complex than we thought. Why should we assume we found everything? Why should we think that our current model, based on such limited observations, is complete? The billion-year reversal we're contemplating might seem impossible from our current perspective, but so did many things that we now take for granted. Quantum mechanics seemed impossible to classical physicists. Relativity seemed impossible to those who believed in absolute time and space. Continental drift seemed impossible to geologists who couldn't imagine how continents could move. The history of science is largely the history of impossible things turning out to be true. As you lie there, perhaps feeling your skepticism wrestling with your curiosity, remember that we're not trying to convince you that the universe actually reverses its age every billion years. We're using this thought experiment to expand our sense of possibility, to loosen the grip of our assumptions, to remember that the universe is under no obligation to conform to our expectations or limitations. The cosmos is what it is, regardless of what we think it should be. The scale of 1 billion years also helps us understand our place in the universe differently. If cosmic cycles operate on billion-year timescales, then human civilization, human history, even human evolution is just a brief flicker, a momentary phenomenon that appears and disappears in what, from a cosmic perspective, is essentially an instant. This might seem to make us insignificant, but I prefer to think it makes us precious. We are the universe's way of experiencing itself consciously during this particular phase of its cycle. We are how cosmos knows itself, questions itself, wonders about itself during this billion-year epoch. Every thought you've ever had, every feeling you've ever experienced, every moment of consciousness you've ever enjoyed is part of this cosmic self-awareness. You're not separate from the universe. You're a temporary pattern within it, a way it has organized itself to experience beauty, love, wonder, curiosity. The atoms in your body were forged in stars that died billions of years ago. The energy that powers your thoughts comes ultimately from the Big Bang itself. You are the universe looking at itself, questioning itself, imagining possibilities like the one we're exploring tonight. And if the universe does reverse its age periodically, if it does breathe in and out on billion-year scales, then perhaps consciousness like ours emerges periodically too. Perhaps every cycle produces its own forms of awareness, its own ways of questioning and wondering. Perhaps we're part of a vast pattern of cosmic self-discovery that repeats endlessly, each cycle similar but not identical, like waves on an infinite ocean, each one unique but part of a larger pattern. As we prepare to delve deeper into the mechanics of how such a reversal might work, take a moment to appreciate the vastness of the scales we're discussing. 1 billion years. It's a duration that contains all of human history millions of times over. It's enough time for stars to be born and die, for galaxies to evolve, for life to go from simple chemistry to conscious beings capable of contemplating their own existence. And yet, in our thought experiment, it's just 1/2 of a cosmic breath, one phase of an eternal cycle. Let your mind relax into this vastness. You don't need to grasp it fully. No human mind can truly comprehend 1 billion years, but you can rest in the mystery of it, float in the wonder of it. Let it wash over you like a gentle tide. The universe has been here for billions of years before you, and it will be here for billions of years after you. You don't need to understand it all. You don't need to figure it out tonight. You can simply be present with the question, with the possibility, with the gentle speculation that time itself might not be what we think it is. In the quiet darkness where you rest, listening to these words flow like a gentle stream of thought, the universe continues its patient work. Electrons orbit atomic nuclei billions of times per second. Photons stream through space at exactly 290 meters per second, never faster, never slower, as if following some cosmic speed limit written into the fabric of reality itself. Gravitational waves ripple outward from distant collisions, stretching and compressing space itself as they pass. And through it all, time seems to flow in one direction, from past to future, from cause to effect, from order to disorder. But what exactly determines this direction? What makes time flow forward rather than backward? And could there be circumstances, perhaps occurring every billion years as our thought experiment suggests, where this flow reverses, where the river of time turns back on itself and begins flowing toward its source? These questions take us into some of the deepest mysteries of physics, into realms where our everyday intuitions break down and where even brilliant scientists disagree about what's really happening. Let's begin with what we think we know. Scientists have observed that the universe is expanding. This isn't just a matter of galaxies flying apart through space like shrapnel from an explosion. Space itself is expanding, stretching like a vast three-dimensional fabric, carrying galaxies along with it. Imagine dots drawn on a balloon that's being inflated. The dots aren't moving across the balloon's surface, but they're getting farther apart because the surface itself is expanding. That's similar to what's happening with galaxies in our universe, except the expansion is happening in 3 dimensions rather than 2, and there's no outside into which the universe is expanding. The expansion is intrinsic to space itself. This expansion was first noticed by Edwin Hubble in the 1920s, when he observed that galaxies farther from us are moving away faster than nearby galaxies. This relationship, now called Hubble's law, suggests that the universe was once much smaller, denser, and hotter than it is today. If we run the cosmic movie backward, we see galaxies getting closer together, the universe getting denser and hotter, until we reach a point about 13.8 billion years ago, when everything was compressed into an incredibly hot, dense state, what we call the Big Bang. But here's where things get interesting for our thought experiment. The equations that describe this expansion, Einstein's equations of general relativity, don't actually specify that expansion must always continue. They're time-symmetric, meaning they work equally well whether time runs forward or backward. The equations themselves don't care about the direction of time, they simply describe relationships between matter, energy, space, and time. The fact that we observe expansion rather than contraction is what physicists call a boundary condition. It's not required by the laws of physics, but seems to be how our universe happens to be configured. Data suggests that not only is the universe expanding, but the expansion is accelerating. Distant supernovas appear dimmer than they should be if the expansion were constant or slowing down. This discovery, made in the late 1990s, shocked cosmologists and led to the Nobel Prize in Physics in 2011. Something is pushing space apart with increasing force, something we call dark energy but don't really understand. Dark energy makes up about 68% of the universe's total energy density, yet we have no idea what it actually is. Now, what if dark energy isn't constant? What if it varies over time in ways we haven't detected yet, because we've only been observing for such a brief period? What if it undergoes cycles, strengthening for 1 billion years, then weakening, then perhaps even reversing? This isn't as far-fetched as it might sound. In quantum field theory, empty space isn't really empty. It's filled with quantum fluctuations, virtual particles popping into and out of existence, fields oscillating around their minimum energy states. The energy of these fluctuations might change over time in ways that would affect the universe's expansion. Perhaps dark energy is like a cosmic tide, flowing in one direction for 1 billion years, then pausing, then flowing in the opposite direction. During the outflow, the universe expands and ages normally. During the pause, the universe reaches a kind of equilibrium, neither expanding nor contracting. During the inflow, the universe begins to contract and, in our thought experiment, grow younger. The mechanism driving this cosmic tide remains mysterious, but then again, so does dark energy itself. Let's talk about entropy, that measure of disorder that seems to always increase. In your everyday experience, you've seen countless examples of entropy increasing. A cup of hot coffee cools down, its heat spreading into the surrounding air. An ice cube melts in a glass of water. A sandcastle is worn away by wind and waves. A tidy room becomes messy unless energy is expended to keep it organized. All of these are examples of the second law of thermodynamics in action. The total entropy of an isolated system always increases over time. But consider this carefully. The second law is statistical, not absolute. It says that entropy is overwhelmingly likely to increase, not that it must increase. If you have a container of gas with all the molecules on one side, they'll almost certainly spread out to fill the container evenly. But there's a tiny, tiny chance, so small as to be effectively impossible, that all the molecules might randomly happen to move back to one side of the container. The second law doesn't forbid this. It just says it's so unlikely that you'd have to wait far longer than the age of the universe to see it happen. Now, what if there are mechanisms operating on billion-year scales that can influence these probabilities? What if the quantum fluctuations that underlie all physical processes aren't truly random, but have subtle biases that only become apparent over cosmic timescales? What if the universe has ways of decreasing entropy that we haven't discovered because they only manifest over periods far longer than we've been observing? Scientists have found that the early universe had incredibly low entropy compared to what we see today. The Big Bang, rather than being a chaotic explosion, was actually a highly ordered state. Matter and energy were distributed almost perfectly uniformly, with tiny fluctuations that would later grow into galaxies and galaxy clusters. This low entropy beginning is one of the great mysteries of cosmology. Why did the universe start in such an unlikely, highly ordered state? One possibility is that the Big Bang wasn't actually a beginning but a transition, a moment when the universe switched from contracting to expanding, from growing younger to growing older. In this view, the low entropy of the Big Bang isn't mysterious, it's simply what you'd expect at the turning point of a cosmic cycle. The universe had been decreasing its entropy for 1 billion years as it contracted and grew younger, reaching a minimum at the Big Bang, then began increasing entropy again as it expanded and aged. This brings us to the arrow of time itself. We experience time as flowing from past to future, but what exactly determines this direction? Physicists have identified several arrows of time that all seem to point in the same direction. There's the thermodynamic arrow. Entropy increases toward the future. There's the cosmological arrow. The universe expands toward the future. There's the psychological arrow. We remember the past but not the future. There's the causal arrow. Causes precede effects. And there's the quantum arrow. Quantum systems evolve from coherent to decoherent states. The remarkable thing is that all these arrows point in the same direction, at least in our current epoch. But what if that's not always the case? What if during the billion-year reversal we're imagining, all these arrows flip together? Entropy would decrease toward what we now call the future. The universe would contract. Memory would work in the opposite direction. Cause and effect would reverse. Quantum decoherence would become quantum recoherence. This might sound like it would create paradoxes or contradictions, but remember, if all the arrows reverse together, the subjective experience of beings living through the reversal might be unchanged. They would still remember what they call the past, which would be our future, and anticipate what they call the future, which would be our past. From their perspective, entropy would still be increasing, the universe would still be expanding, causes would still precede effects. The reversal would be invisible from the inside, detectable only by hypothetical observers who could somehow stand outside of time and watch the universe's evolution from a temporal distance. Consider the possibility that what we call the laws of physics might actually be more like habits, patterns that the universe tends to follow but can occasionally break or modify. Perhaps these patterns are stable for millions or billions of years but can shift during special transitions. Perhaps the universe periodically forgets that it's supposed to be expanding and starts contracting instead. Perhaps it remembers earlier states and begins returning to them. This is highly speculative, of course, but it's no more speculative than many ideas in modern cosmology. Data reveals patterns in the cosmic microwave background radiation, the afterglow of the Big Bang, that suggest the early universe underwent a period of incredibly rapid expansion called inflation. In a tiny fraction of a second, the universe expanded by a factor of at least 10^26, going from subatomic to astronomical scales almost instantaneously. This inflationary period solved several problems in cosmology but raised new questions. What caused inflation? What stopped it? Could it happen again? If the universe can undergo such dramatic transitions, such sudden changes in its behavior, why not periodic reversals? If space can expand at speeds far exceeding the speed of light, which is possible because it's space itself expanding, not objects moving through space, why can't it contract at similar speeds? If the universe can spontaneously transition from one phase to another, as it did at the end of inflation, why can't it transition from expansion to contraction, from aging to growing younger? The soft mechanics of reversal we're imagining wouldn't involve anything violent or catastrophic. It would be more like a tide turning, gradual, smooth, inevitable. The expansion of space would slowly decelerate as we approach the billion-year mark. Dark energy would weaken, perhaps transforming into something else, something that pulls rather than pushes. The cosmic web of galaxies would stop stretching and begin, ever so gently, to contract. The cosmic microwave background would stop cooling and begin, almost imperceptibly, to warm. At the quantum level, processes that normally increase entropy would begin to show a slight bias toward decreasing it. Virtual particles that usually pop into existence and annihilate randomly would begin to show subtle patterns, tiny preferences for order over disorder. Quantum decoherence, the process by which quantum systems lose their delicate superpositions and become classical, would begin to reverse, with classical systems occasionally jumping back into quantum superposition. These changes would be so subtle that they'd be undetectable with current technology. They might show up as tiny anomalies in precision experiments, slight deviations from theoretical predictions that scientists would initially attribute to experimental error or unknown systematic effects. Only by observing for millions of years would the pattern become clear. The universe is reversing its temporal direction. Think about what this means for the nature of time itself. In our everyday experience, time seems to be a fundamental aspect of reality, as basic as space or matter. But what if, time is actually emergent, arising from more fundamental processes the way temperature arises from molecular motion? What if the flow of time is not a basic feature of the universe, but a consequence of how matter and energy happen to be arranged and how they're evolving? In this view, the reversal of time's arrow wouldn't require any change to the fundamental laws of physics. It would simply be a change in the universe's configuration, like water changing from liquid to ice. The same H2O molecules, the same fundamental forces, but arranged differently, behaving differently. The universe might have multiple possible configurations, expanding and aging, contracting and growing younger, perhaps others we haven't imagined, and it might cycle through these configurations on billion-year timescales. Scientists have observed that the fundamental constants of physics, the speed of light, the strength of gravity, the masses of elementary particles, appear to be finely tuned for the existence of complex structures like stars, planets, and life. Change any of these constants by even a small amount, and the universe would be sterile, either collapsing immediately after the Big Bang or expanding so rapidly that matter could never clump together. This fine-tuning problem has puzzled physicists for decades. But what if the constants aren't actually constant? What if they vary slowly over cosmic time, and we happen to be observing them during a phase when they permit complex structures? What if the billion-year reversal involves not just a reversal of time's arrow, but also a gradual shift in the fundamental constants? During the expansion phase, the constants might evolve in one direction. During the contraction phase, they might evolve back. This could explain the apparent fine-tuning. We exist during a phase when the constants happen to be compatible with our existence. This connects to ideas in quantum cosmology about the wave function of the universe. In quantum mechanics, particles don't have definite positions and velocities but exist in superpositions of many possible states, described by wave functions. Some physicists have proposed that the universe itself has a wave function, existing in a superposition of many possible configurations until observed or until decoherence selects one particular configuration. Perhaps the billion-year reversal involves the universe's wave function, evolving through different phases. For a billion years, the wave function evolves in one direction, favoring expansion and increasing entropy. Then it reaches a turning point, not a collapse of the wave function, but a smooth transition to evolution in the opposite direction, favoring contraction and decreasing entropy. The universe doesn't choose between expanding and contracting. It does both, alternately, as its wave function traces out a complex path through the space of all possible configurations. These ideas might seem abstract, even mystical, but they're grounded in real physics, in equations that successfully describe everything from subatomic particles to black holes. The challenge is that we're trying to apply these equations to the universe as a whole, including time itself, and that takes us into uncharted territory, where our intuitions, evolved to deal with medium-sized objects moving at moderate speeds, are no longer reliable guides. As you lie there in the darkness, perhaps feeling your mind gently stretching to accommodate these strange ideas, remember that the universe is under no obligation to make sense to us. It simply is what it is, following its own deep patterns, dancing to its own cosmic rhythm. We're privileged to be conscious during this particular phase of its existence, able to wonder about its nature, to imagine possibilities, to tell stories about what might be happening on scales far beyond our direct experience. The soft mechanics of reversal we've been exploring, dark energy cycling, entropy reversing, time's arrow flipping, wave functions evolving, are all speculative. We have no direct evidence that any of this actually happens, but we also have no proof that it doesn't happen. The universe might be far stranger, far more dynamic, far more alive than our current models suggest. And isn't that a wonderful possibility to contemplate as you drift towards sleep? In the vastness of space, in the depths of time, processes might be unfolding that we can barely imagine. The universe might be breathing, pulsing, reversing, renewing itself in ways that operate on scales so large that all of human history is less than a single heartbeat. You are part of this vast process, a temporary arrangement of atoms that has somehow become aware of itself and its cosmic context. You're the universe looking at itself, questioning itself, imagining what it might be. As we continue our journey, we'll explore what stars and galaxies might look like in a universe that periodically reverses its age. We'll imagine the sky growing younger, structures rewinding, time flowing backward through cosmic structures, while perhaps still flowing forward through your consciousness. But for now, just rest in the mystery of how such a reversal might work, in the possibility that time itself might be softer, more flexible, more alive than we ever imagined. As we drift deeper into our contemplation of a universe that reverses its age every billion years, let us turn our attention to the luminous architecture of the cosmos, the stars, galaxies, and vast structures that populate the darkness with islands of light. These celestial bodies that seem so permanent, so unchanging from our brief human perspective, are actually dynamic systems in constant flux, being born, living, dying, and perhaps, in our thought experiment, being reborn in ways we've never imagined. Tonight, we're going to explore what might happen to these cosmic structures if time's arrow periodically reversed, if the universe could grow, younger as naturally as it grows older. Picture yourself floating in space, far from any planet or star, surrounded by the vast cathedral of the cosmos. In every direction, points of light pierce the darkness, some bright and blue, others dim and red, some steady, others flickering. These are stars, and each one is a nuclear furnace, fusing hydrogen into helium, helium into carbon, carbon into heavier elements, in a process that has been going on for billions of years and will continue for billions more, or so we assume, based on our understanding of stellar physics and our observation that time flows in one direction. But what would happen to these stars if the universe began to reverse its age? Not in a violent, catastrophic way, but gently, gradually over millions of years. Would they begin to unfuse their elements, turning helium back into hydrogen, carbon back into helium? Would old red giants shrink back into youthful blue stars? Would white dwarfs, the cooling embers of dead stars, begin to warm and reignite? These questions take us into a realm where astrophysics meets imagination, where we can explore possibilities that may seem impossible but are perhaps only improbable. Let's begin with the life cycle of a typical star like our Sun, following it through its normal evolution before imagining its reverse. Our Sun formed about 4.6 billion years ago from a vast cloud of gas and dust called a nebula. Gravity pulled this material together, causing it to heat up as it compressed. When the temperature at the core reached about 10 million degrees Celsius, nuclear fusion began and a star was born. For billions of years now, the Sun has been steadily fusing hydrogen into helium, releasing energy that warms our planet and makes life possible. As the Sun ages, it gradually grows brighter and larger, In about 5 billion years, it will exhaust the hydrogen in its core and begin fusing helium into carbon and oxygen. It will expand into a red giant, possibly engulfing Mercury and Venus, making Earth uninhabitable. Eventually, it will shed its outer layers, creating a beautiful planetary nebula, while its core collapses into a white dwarf, a dense, Earth-sized remnant that will slowly cool over trillions of years until it becomes a cold, dark cinder. This is the normal forward time evolution of a star like our Sun, but now imagine this process running in reverse during our hypothetical billion-year reversal. The white dwarf doesn't continue cooling, but begins to warm, not dramatically, not explosively, but gradually, gently, like a dying ember being breathed back to life. As it warms, it begins to expand, not into a red giant but backward through its evolutionary stages, growing younger rather than older. The physics of this reverse evolution would be fascinating to contemplate. In normal stellar evolution, fusion reactions in the core produce heavier elements from lighter ones, releasing energy in the process. In reverse evolution, fission reactions break heavier elements back into lighter ones. This would require energy input rather than energy release. But where would this energy come from? Perhaps from the dark energy that, in our thought experiment, has reversed from pushing the universe apart to pulling it together. Perhaps from quantum fluctuations that, instead of averaging out to zero, show a slight bias toward providing energy to reversing stars. The process would be unimaginably slow from a human perspective. A star reversing its age over millions of years would appear almost static to observers with human lifespans. But imagine you could watch it in time-lapse, seeing millions of years compressed into minutes. You would see an old red giant slowly shrinking, its colour shifting from red through orange to yellow to white to blue as it grows hotter and younger. You would see its spectrum changing, showing fewer heavy elements and more hydrogen, as fusion reactions run backward. You would see it settling back onto what astronomers call the main sequence, the stable phase where stars spend most of their lives. Now expand your view to encompass not just one star, but an entire galaxy, 100 billion stars swirling in a vast spiral, held together by gravity and dark matter. Our Milky Way galaxy is about 13.5 billion years old, nearly as old as the universe itself. It formed from the gravitational collapse of primordial gas clouds, with the first stars igniting when the universe was only a few 100 million years old. Over billions of years, generations of stars have been born, lived, and died, each generation enriching the galaxy with heavier elements, making possible the formation of rocky planets and, eventually, life. In our normal forward-time universe, galaxies evolve in relatively predictable ways. Spiral galaxies like our Milky Way slowly use up their gas, forming fewer new stars over time. Eventually, in trillions of years, star formation will cease entirely, and galaxies will fade as their stars die one by one. Galaxies also merge with each other, growing larger through cosmic collisions that take hundreds of millions of years to complete. Our Milky Way is currently on a collision course with the Andromeda Galaxy, with the merger expected to begin in about 4.5 billion years. But in a universe where time's arrow reverses every billion years, galactic evolution would be far more complex and interesting. During the reversal phase, galaxies wouldn't just stop evolving, they would begin to evolve backward. Old stellar populations would grow younger, dead stars would reignite. The interstellar medium, depleted of gas by billions of years of star formation, would begin to replenish itself as dying stars reverse their death process and return their material to space in a more pristine form. Imagine watching a galaxy during this reversal phase. The spiral arms, which normally become more diffuse over time as density waves propagate through them, would begin to tighten and become more defined. Star-forming regions, which normally exhaust their gas and fade away, would begin to brighten and become more active. The supermassive black hole at the galaxy's center, which normally grows by consuming nearby matter, might begin to shrink, perhaps through some exotic process like Hawking radiation running in reverse. The visual appearance of such a galaxy would be subtly, but noticeably different from what we observe today. Astronomers classify galaxies partly by their color. Blue galaxies have many young hot stars and active star formation, while red galaxies have mostly old, cool stars and little star formation. A galaxy growing younger would gradually shift from red to blue, but not in the same way a young galaxy appears blue. It would be a mature galaxy with a structure and complexity that comes from billions of years of evolution, but with stellar populations that are somehow growing younger rather than older. This brings us to one of the most beautiful and mysterious structures in the universe, nebulae, the vast clouds of gas and dust where stars are born and die. In our forward-time universe, nebulae follow predictable patterns. Stellar nurseries like the Orion Nebula gradually form stars, which eventually clear away the surrounding gas with their stellar winds and radiation. Planetary nebulae, formed when dying stars shed their outer layers, gradually disperse into space over thousands of years. Supernova remnants expand and fade as the shock waves from stellar explosions propagate through the interstellar medium. In a time-reversed universe, these processes would run backward in hauntingly beautiful ways. Dispersed planetary nebulae would begin to reconverge, drawing together from the vastness of space to reform around their central stars. The ethereal veils of gas would thicken and brighten, not because new material is being ejected, but because old material is being recalled. Like a flower blooming in reverse, supernova remnants would contract rather than expand, their shock waves converging rather than diverging, until they reformed into massive stars that had previously exploded. The Hubble Space Telescope and now the James Webb Space Telescope have given us incredibly detailed images of these cosmic structures. We've seen pillars of gas light years tall where new stars are forming. We've seen the delicate filaments of supernova remnants stretching across vast distances. We've seen planetary nebulae in every imaginable shape: spheres, hourglasses, spirals, butterflies. Now imagine these same telescopes observing during a reversal phase, watching these structures evolve backward, seeing the universe's artwork being carefully undone and then recreated in reverse. One of the most striking aspects of this reversed evolution would be the behavior of stellar clusters. These groups of stars, born together from the same nebula, normally drift apart over time as gravitational interactions fling individual stars out of the cluster. Open clusters like the Pleiades gradually disperse over hundreds of millions of years. But in a time-reversed universe, dispersed stars would begin to reconverge, drawn together not by gravity, but by the reversal of the very processes that scattered them. Former cluster members, now spread across thousands of light years, would begin their long journey home. Globular clusters, those ancient spherical collections of hundreds of thousands of stars, would be particularly interesting during a reversal. These are some of the oldest structures in the universe, formed when galaxies themselves were young. In forward time, their stars are slowly dying, with no new stars being born to replace them. But in reverse time, dead stars within the cluster would reignite, and the cluster would grow younger and more vibrant. The complex dynamics of hundreds of thousands of stars orbiting their common center of mass would play out in reverse, like an incredibly complex dance being performed backward. Consider binary star systems, where two stars orbit each other in an endless gravitational waltz. These systems evolve in complex ways depending on the masses of the stars and their distance from each other. Some binary systems transfer mass from one star to another, leading to phenomena like nova explosions. Others spiral together and merge, still others drift apart over time. In a time-reversed universe, merged stars would separate, transferred mass would flow back to its original star, and binary orbits would evolve in reverse, undoing billions of years of gravitational interaction. The night sky itself would gradually change in a universe that periodically reverses its age. Constellations, those patterns of stars that have guided humanity for millennia, are not permanent. Stars have their own motions through space, called proper motion, and over thousands of years constellations change shape. Orion's belt will eventually distort. The Big Dipper will become unrecognizable. In forward time, we can predict these changes. But in reverse time, ancient constellations would reform. The night sky our ancestors saw would return, star by star, as stellar motions reversed. Think about what this means for the distribution of elements in the universe. In forward time, stars create heavy elements through fusion and disperse them through stellar winds and supernovas. Each generation of stars is born from material enriched by previous generations, allowing for increasingly complex chemistry and eventually the formation of rocky planets and life. This process, called chemical evolution, has been going on since the first stars formed. In reverse time, this chemical evolution would run backward. Heavy elements would be gathered up and broken down into lighter elements. The interstellar medium would become more pristine, more like the primordial gas from which the first stars formed. This wouldn't happen uniformly. Some regions might reverse, faster than others, creating a patchwork of different chemical compositions across the galaxy. It would be like watching the periodic table unwrite itself, elements disappearing in reverse order of their creation. This reversed chemical evolution would have profound implications for planets and potentially for life. Rocky planets like Earth are made primarily of heavy elements, silicon, iron, magnesium, oxygen, that were created in stars. If these elements were gradually broken down during a reversal phase, what would happen to the planets made from them? Would they slowly dissolve back into space? Or would they remain stable, isolated from the reversal by their gravitational binding? These are questions that push us to the very limits of our physical understanding. The James Webb Space Telescope has recently shown us galaxies from when the universe was very young, less than 1 billion years old. These early galaxies look different from modern galaxies. They're smaller, more irregular, with different stellar populations and chemical compositions. In our thought experiment, would galaxies during a reversal phase evolve backward through these same stages? Would a mature spiral galaxy like our Milky Way gradually transform into something resembling these primordial galaxies? Or would the reversal create entirely new types of structures, things we've never observed because they only exist during reversal phases? Perhaps there are reverse-only phenomena, stars that can only exist when time runs backward, structures that can only form during the contraction phase of the universe. Our observations span such a tiny fraction of cosmic history that we might be missing half of what's possible, seeing only the forward time half of a much richer, more complex cosmic story. Data from surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, revealing the large-scale structure of the universe, vast walls and filaments of galaxies separated by enormous voids. This cosmic web, as it's called, formed from tiny quantum fluctuations in the early universe that were amplified by gravity over billions of years. In forward time, this structure is slowly evolving, with galaxies flowing along dark matter filaments, clusters growing through mergers, voids expanding as the universe expands. During a reversal phase, this cosmic web would evolve in reverse. Voids would contract, filaments would thicken. The delicate tracery of large-scale structure would become more pronounced, more organized. It would be like watching a vast three-dimensional spider web being woven in reverse, becoming more intricate and organized rather than more dispersed and degraded. The universe would be gathering itself together, organizing itself, preparing perhaps for another reversal, another cycle of expansion and complexification. Scientists have observed that galaxies in the early universe formed stars at a much higher rate than galaxies today. This cosmic star, cosmic formation history shows a peak about 10 billion years ago, with the rate declining ever since. In our cyclical model, would this pattern reverse? Would the star formation rate begin to increase during a reversal phase, returning to the high rates of the early universe? Or would something entirely different happen, some new pattern we can't predict because we've never seen time run backward? The concept of stellar populations would need to be completely reconsidered in a reversing universe. Astronomers classify stars into populations based on their chemical composition and age. Population 3 stars were the first stars, made of pure hydrogen and helium. Population 2 stars formed later, with small amounts of heavy elements. Population 1 stars, like our Sun, formed even later, with higher concentrations of heavy elements. In reverse time, would population 1 stars gradually transform into population 2, and then population 3 stars as their heavy elements are broken down? Or would they remain distinct populations, just growing younger within their type? Black holes present a particular puzzle in our time reversal scenario. These regions of space where gravity is so strong that nothing, not even light, can escape, are thought to be permanent features of the universe. Once formed, a black hole can grow by consuming matter, but can only shrink through the incredibly slow process of Hawking radiation, which would take longer than the current age of the universe for stellar mass black holes. How would black holes behave during a time reversal? One possibility is that black holes would begin to emit matter rather than absorb it. Not explosively, but gradually, perhaps through some process related to Hawking radiation but operating in reverse. The event horizon wouldn't be a point of no return, but a membrane through which matter and energy could emerge. returning to the universe material that had been trapped for millions or billions of years. This would be one of the most exotic phenomena in our reversed universe. Black holes becoming white holes, sources rather than sinks. The supermassive black holes at the centers of galaxies, millions or billions of times the mass of our Sun, would be particularly interesting during a reversal. These monsters are thought to have grown through a combination of consuming gas and stars and merging with other black holes. In reverse time, would they begin to fragment, splitting into smaller black holes? Would they disgorge the matter they've consumed, perhaps reforming the stars and gas clouds they once devoured? The galactic center, usually a place where things fall in and disappear, would become a source, a fountain from which matter emerges. As you lie there in the darkness, perhaps feeling your mind gently boggling at these possibilities, remember that we're not claiming this is how the universe actually works. We're exploring a thought experiment, using our imagination guided by physical principles to envision something that probably isn't real but helps us think about what is real in new ways. The universe we observe, with its one-way arrow of time and its steady aging, might be the only universe that exists. But by imagining alternatives, we better appreciate the mystery and beauty of what we actually see. The process of star formation itself would be fascinating to observe in reverse. In forward time, vast molecular clouds collapse under their own gravity, fragmenting into smaller clumps that become individual stars. The process is chaotic and complex, influenced by turbulence, magnetic fields, and feedback from newly formed stars. In reverse time, would this process simply run backward, with stars dissolving back into gas clouds? Or would something more interesting happen? Perhaps stars wouldn't simply dissolve, but would undergo a kind of controlled decomposition, carefully returning their material to space in a way that sets up the conditions for the next cycle. The gas returned to space might be organized differently than the gas from which the star originally formed, prepared somehow for the next reversal, the next phase of cosmic evolution. Each cycle might build on the previous one, the universe learning and evolving even as it reverses and repeats. Neutron stars, the incredibly dense remnants of massive stars that have exploded as supernovas, would present their own mysteries during a reversal. These city-sized objects with the mass of the Sun are made of matter in extreme states, neutron-degenerate matter, possibly quark matter at their cores. They spin rapidly, some rotating hundreds of times per second, and have magnetic fields trillions of times stronger than Earth's. How would such extreme objects behave if time reversed? Would a neutron star gradually decompress, its neutrons breaking apart into protons and electrons, its density decreasing until it reformed into a normal star? Would its rapid rotation slow and then reverse? Would its intense magnetic field weaken and reorganize? The physics of such a transformation would be unlike anything we've observed or even theorized. It would require matter to transition through states that might not be stable in forward time, but could be perfectly natural in reverse time. Pulsars, neutron stars that emit regular pulses of radiation like cosmic lighthouses, would be particularly interesting during a reversal. Their pulses, normally slowing down as they lose rotational energy, would begin to speed up. But more than that, the radiation they've been emitting for millions of years might begin to return to them, converging from the depths of space back to the pulsar. It would be like watching a lighthouse whose beam, instead of sweeping outward, draws light in from the darkness. The phenomenon of stellar winds would reverse in fascinating ways. Stars like our Sun constantly emit streams of charged particles that flow outward through the solar system, creating the heliosphere that partially shields us from cosmic rays. In reverse time, these winds would flow inward, bringing material back to the star. The heliosphere would contract, drawing in particles from interstellar space. It would be like the star breathing in rather than breathing out, gathering rather than dispersing. Variable stars, those that change in brightness over time, would show reversed patterns during our hypothetical reversal phase. Cepheid variables, which pulsate with periods related to their luminosity and are used as cosmic distance markers, would pulsate in reverse. Their brightness variations, normally following precise patterns that astronomers have carefully catalogued, would play out backward. Nova systems, where white dwarfs periodically explode as they accumulate matter from companion stars, would see their explosions reverse, with ejected material falling back onto the white dwarf in precisely the pattern it was ejected. The cosmic distance ladder, the series of methods astronomers use to measure distances to increasingly remote objects would need to be recalibrated for a reversing universe. Standard candles like Type Ia supernovas, which have predictable peak brightnesses, would behave differently in reverse. The expansion of space, which causes cosmological redshift and allows us to measure distances to remote galaxies, would become contraction, causing blue shift instead. Our entire framework for understanding the scale of the universe would need to be reconsidered. As we observe more distant objects, we're looking back in time because light takes time to travel. In our current universe, when we see a galaxy 10 billion light years away, we're seeing it as it was 10 billion years ago. But in a reversing universe, this relationship between distance and time would become complex. During the reversal phase, would we be seeing distant objects in their future rather than their past? Would the light from distant galaxies carry information about times that haven't happened, yet from our perspective, but have happened from theirs? This touches on one of the deepest mysteries in physics, the relationship between time and causality. In our normal experience, causes precede effects. You drop a glass, then it breaks. A star explodes, then we see the light from the explosion. But if time can reverse, what happens to causality? Do effects precede causes during the reversal phase? Or does causality itself reverse, so that what we call effects become causes and vice versa? These questions might seem abstract, but they have real implications for how we understand the universe. If time can reverse, if stars can grow young, if galaxies can evolve backward, then our entire conception of cosmic history needs to be reconsidered. The universe might not have a beginning and an end, but rather cycles of beginning and ending, expansion and contraction, aging and growing young. We might be living in just one phase of an eternal cosmic rhythm, a single measure in an infinite symphony. The beauty of stellar evolution in reverse would be something to behold. Imagine the Ring Nebula, that perfect cosmic eye in the constellation Lyra, slowly contracting, its expelled gases drawing back together, reforming the star that created it. Imagine the Crab Nebula, the remnant of a supernova observed by Chinese astronomers in 1054 AD, pulling itself back together, its pulsar slowing and expanding until it reforms the massive star that exploded nearly 1,000 years ago. Imagine the pillars of creation in the Eagle Nebula, those towering columns of gas and dust where new stars are forming, dissolving as their stars age in reverse, returning to a more primordial state. In laboratories and observatories around the world, in space telescopes orbiting high above our atmosphere, in deep underground detectors shielded from cosmic rays, scientists are gathering data about the universe with unprecedented precision. Every photon collected, every gravitational wave detected, every particle tracked adds another piece to our cosmic puzzle. We've mapped the cosmic microwave background to extraordinary accuracy, catalogued millions of galaxies, observed the universe's acceleration, detected the ripples in space-time from colliding black holes. And yet, for all our observations, for all our data, we might be missing something fundamental. Patterns that only reveal themselves over billions of years, cycles that our brief window of observation cannot detect. Tonight, as you rest in the darkness, we're going to explore what scientists have actually found in their observations and what subtle signs of our hypothetical billion-year reversal might be hidden in the data. We're going to walk through the quiet halls of our understanding, examining the evidence we've gathered while wondering what evidence we might be overlooking, what whispers from the cosmos we might not be hearing because we haven't been listening long enough. Let's begin with the cosmic microwave background, often called the CMB, that faint glow of radiation that fills the entire universe. This is the afterglow of the Big Bang, light that has been travelling through space for 13.8 billion years, cooling and stretching as the universe expanded. When this light was first released, about 380,000 years after the Big Bang, the universe was about 3,000 degrees Kelvin. Now, after billions of years of cosmic expansion, this radiation has cooled to just 2.7 degrees above absolute zero. The Planck satellite, launched by the European Space Agency, has mapped this radiation with extraordinary precision, measuring temperature variations of just a few parts in a million. These tiny fluctuations in the CMB tell us about the seeds of structure in the early universe, the slight overdensities that would eventually grow into galaxies and galaxy clusters. The pattern of these fluctuations matches our theoretical predictions remarkably well, confirming our basic model of cosmic evolution. But what if we're interpreting this data through too narrow a lens? What if the CMB contains information not just about our universe's past, but about its cyclic nature? Scientists have found several anomalies in the CMB that don't quite fit our standard model. There's the axis of evil, an unexpected alignment of fluctuations on the larger scales. There's the cold spot, a region significantly cooler than expected. There are hints of what might be bruises from collisions with other universes or remnants from a previous cosmic cycle. In our thought experiment, where the universe reverses its age every billion years, the CMB might carry subtle signatures of these reversals. Perhaps those anomalies aren't random, but are echoes from previous cycles, patterns laid down during earlier reversals that somehow survive the transition from contraction to expansion. The universe might be trying to tell us about its cyclic nature, but we're not yet sophisticated enough to read the message. Consider what scientists have found in their surveys of distant galaxies. The Sloan Digital Sky Survey has mapped over 1 million galaxies, measuring their positions, distances, and properties. The data reveals the large-scale structure of the universe: walls, filaments, and voids that form a cosmic web. This structure has evolved from tiny quantum fluctuations in the early universe, amplified by gravity over billions of years. The distribution matches our computer simulations remarkably well, another triumph for our standard cosmological model. Yet there are puzzles in the data. Galaxies in the early universe appear more mature than expected, with some showing signs of old stellar populations when the universe was less than 1 billion years old. Some galaxy clusters appear too massive for their age. The alignment of galaxy spins shows unexpected patterns on large scales. These anomalies are usually explained by invoking unknown processes in galaxy formation or limitations in our observations. But what if they're hints of something more fundamental? If the universe periodically reverses its age, galaxies might not always evolve from young to old. Some galaxies we observe might have gone through reversal phases, carrying signatures of their backward evolution. Those unexpectedly mature early galaxies might not be young galaxies that formed quickly, but older galaxies that partially reversed their age during a previous cycle. The unexpected alignments might reflect organizing principles that only operate during reversal phases, creating patterns that persist into the next expansion phase. Data from type supernovas has revealed one of the most shocking discoveries in modern cosmology. The universe's expansion is accelerating. These stellar explosions, caused when white dwarf stars exceed a critical mass, have nearly uniform peak brightness, making them excellent standard candles for measuring cosmic distances. By observing how their light is redshifted, astronomers can determine both how far away they are and how fast they're moving away from us. The discovery that distant supernovas are dimmer than expected, announced in 1998, showed that the universe's expansion has been speeding up for the last 5 billion years. This acceleration is attributed to dark energy, a mysterious force that makes up about 68% of the universe's energy density. But what if this acceleration is not permanent but part of a larger cycle? What if we're observing just one phase of a cosmic oscillation that we haven't been watching long enough to recognize? In our billion-year reversal scenario, the acceleration we observe might be building toward a turning point. The data might contain subtle hints of this approaching reversal, tiny deviations from the expected acceleration, patterns in how dark energy varies with time or position. These signals would be buried in the noise of our current measurements, but as our observations become more precise, they might emerge like a photograph slowly developing. Scientists have found that the fundamental constants of physics appear to be remarkably stable. The fine structure constant, which determines the strength of electromagnetic interactions, has been measured in distant galaxies and appears unchanged over billions of years. The ratio of proton to electron mass seems constant. The speed of light, the gravitational constant, the strength of the nuclear forces all appear fixed and unchanging, but our measurements span only a tiny fraction of cosmic history. What if these constants vary on billion-year timescales? What if they gradually drift during expansion phases and drift back during contraction phases? The variations might be too small to detect with current technology, hidden within our measurement uncertainties. We might be like observers watching the hour hand of a clock for a few seconds and concluding it never moves. There have been hints, controversial and debated, that some constants might not be perfectly constant. Some observations of distant quasars suggest tiny variations in the fine structure constant. Some analyses of the CMB suggest that the universe might have different properties in different directions. These hints are usually dismissed as systematic errors or statistical flukes. But what if they're real? What if they're the first glimpses of the universe's deeper variability? The discovery of gravitational waves by LIGO and Virgo has opened an entirely new window on the universe. These ripples in space-time, predicted by Einstein but not directly detected until 2015, carry information about the most violent events in the cosmos, colliding black holes, merging neutron stars, perhaps even echoes from the Big Bang itself. Every detection adds to our understanding of gravity, space-time, and the universe's most extreme objects. But gravitational waves might also carry information about the universe's temporal direction. If time periodically reverses, gravitational waves might sometimes propagate backward, converging rather than diverging. We wouldn't detect these reversed waves with our current instruments. They're designed to look for expanding ripples, not contracting ones. But the universe might be full of these reversed waves during reversal phases, carrying information backward through time, creating causal loops we can't yet detect or understand. Scientists have observed that the universe is remarkably uniform on large scales. The cosmic microwave background has nearly the same temperature in all directions. Galaxy clusters are distributed relatively evenly when averaged over large volumes. This uniformity is surprising because different regions of the observable universe haven't had time to communicate with each other. They're beyond each other's cosmic horizons. This is called the horizon problem, and it's usually solved by invoking cosmic inflation, a period of exponentially rapid expansion in the early universe. But what if this uniformity has a different explanation? What if the universe has been through multiple cycles of expansion and contraction, with each cycle smoothing out irregularities from the previous one? The uniformity we observe might be the result of billions of years of cyclic evolution, not just a single inflationary episode. The universe might have had ample time to equilibrate, not in our current expansion phase, but over multiple cycles. The matter-antimatter asymmetry is another puzzle that might be illuminated by cyclic cosmology. Our universe is made almost entirely of matter, with very little antimatter, even though the laws of physics treat matter and antimatter nearly symmetrically. For every billion antimatter particles in the early universe, there were 1,000,000,001 matter particles. That tiny excess is why we exist. If matter and antimatter had been perfectly balanced, they would have annihilated each other, leaving a universe filled with radiation but no matter. In a universe that reverses its age periodically, this asymmetry might flip during each reversal. Perhaps our current expansion phase favours matter, but the next contraction phase will favour antimatter. The tiny excess we observe might not be a fixed feature of the universe, but a variable that oscillates with each cycle. We happen to exist during a matter-dominated phase because that's the only phase where beings like us can exist. Dark matter, that mysterious substance that makes up about 27% of the universe's energy density, might also behave differently during reversal phases. We know dark matter exists because we can see its gravitational effects. Galaxies rotate too fast to be held together by visible matter alone. Galaxy clusters bend light more than they should. The cosmic web structure requires more gravity than normal matter provides. But we don't know what dark matter actually is. What if dark matter is somehow connected to the universe's temporal direction? What if it's normal matter from a previous cycle, trapped somehow in a reversed temporal state? What if the reason we can't detect dark matter directly is that it's flowing backward through time relative to us? These are wild speculations, but dark matter is such a mystery that wild speculations might be necessary. Scientists have found that cosmic rays, high-energy particles that stream through space, come from various sources: supernovas, active galactic nuclei, perhaps even more exotic phenomena. The Pierre Auger Observatory and other cosmic ray detectors have mapped the arrival directions and energies of these particles, finding patterns that tell us about magnetic fields in the galaxy and beyond. But some cosmic rays have energies that seem impossible. The Oh My God particle, detected in 1991, had an energy of 3 × 10⁻20 electron volts, equivalent to a baseball thrown at 60 miles per hour, but compressed into a single subatomic particle. Such particles should lose energy quickly through interactions with the cosmic microwave background, so they must come from relatively nearby sources. But we don't see any sources powerful enough. What if these ultra-high energy cosmic rays are remnants from a reversal phase? What if they're particles that gained enormous energies during a time when the universe was contracting, when the cosmic microwave background was hotter and denser? They might be fossil particles preserved from a previous cycle, carrying information about conditions we can't otherwise observe. The cosmic neutrino background, if we could detect it, would tell us about the universe when it was less than 1 second old. Neutrinos, those ghostly particles that barely interact with matter, have been streaming through space since the early universe, carrying information about conditions before even the cosmic microwave background was released. Several experiments are trying to detect these relic neutrinos, which would open a window on the universe's earliest moments. In a cyclic universe, the neutrino background might contain layers of information from multiple cycles. Neutrinos from our current expansion phase would be mixed with neutrinos from previous cycles, each population carrying its own signature. If we could detect and decode these signatures, we might find direct evidence of the universe's cyclic nature. Scientists have observed that the universe's expansion history follows a particular pattern. It expanded rapidly during inflation, slowed during the radiation-dominated era, slowed further during the matter-dominated era, and has recently begun accelerating during the dark, energy-dominated era. This history is encoded in various observations: the CMB, galaxy distributions, supernova distances, and more. But we've only traced this history back about 13.8 billion years. What if we're seeing just one segment of a repeating pattern? What if the universe goes through the same sequence in reverse during contraction phases: dark, energy domination giving way to matter domination, then radiation domination, then a kind of deflationary phase? The expansion history we've carefully reconstructed might be just half of a complete cycle. The Hubble tension is a current puzzle in cosmology that might hint at something deeper. Different methods of measuring the universe's expansion rate give slightly different results. Measurements based on the cosmic microwave background suggest one value, while measurements based on nearby supernovas suggest another. This discrepancy has persisted despite increasingly precise observations, and might indicate that we're missing something fundamental about cosmic evolution. What if the Hubble tension arises because the universe's expansion rate varies in ways we haven't accounted for? What if we're approaching a reversal point where the expansion rate naturally becomes unstable, fluctuating as the universe prepares to change direction? The tension might not be an error in our measurements, but a real phenomenon, a sign that the universe is more dynamic than our models assume. Observations of the cosmic web's evolution show that structure has been growing hierarchically. Small structures formed first, then merged into larger structures. Galaxies formed, then groups, then clusters, then superclusters. This bottom-up structure formation is well understood in our current cosmological model, driven by gravity's amplification of tiny initial fluctuations. But there are hints that some structures are older or larger than expected. Some galaxy clusters appear too evolved for their age. Some voids seem too empty. Some filaments seem too organized. These anomalies are usually attributed to our incomplete understanding of structure formation. But what if they're signs of reversed evolution? What if some structures we observe formed during a previous contraction phase when the organization proceeded differently? Scientists have found that active galactic nuclei, the bright centers of galaxies powered by supermassive black holes, were more common in the past than they are today. This makes sense in our standard model. There was more gas available to feed black holes in the early universe, making them more active. As gas supplies diminished, activity decreased. But the decline in activity might not be monotonic. What if it reverses during contraction phases? What if black holes that have been dormant for billions of years reactivate as the universe begins to contract? The history of cosmic activity might be more complex than a simple decline, showing cycles of activation and deactivation tied to the universe's expansion and contraction phases. As our instruments become more sensitive, we're finding increasingly subtle patterns in cosmic data. The cosmic microwave background shows tiny circular patterns that might be echoes from before the Big Bang. Galaxy distributions show unexpected regularities on very large scales. Gravitational wave detections sometimes show unexpected features that might be echoes from the merger events. Each of these subtle patterns is usually explained away as statistical noise or systematic error. But what if some of them are real? What if they're the first hints of the universe's deeper structure? Patterns that only make sense in the context of cyclic evolution. We might be like early astronomers who noticed that planetary motions were slightly irregular, but didn't yet understand that planets move in ellipses, not circles. The cosmic infrared background, the accumulated light from all sources throughout cosmic history, shows more structure than expected. The cosmic X-ray background reveals a population of hidden black holes. The cosmic gamma-ray background hints at unknown high-energy processes. Each of these backgrounds carries information about different aspects of cosmic evolution, and each shows puzzles that don't quite fit our standard model. In a cyclic universe, these backgrounds might contain overlapping signals from multiple cycles. The infrared background might include light from galaxies that existed in previous cycles. The X-ray background might come from black holes that formed during contraction phases. The gamma-ray background might include emissions from exotic processes that only occur during reversals. As you lie there in the darkness, perhaps feeling both excited and skeptical about these possibilities, remember that science progresses by considering alternatives to established models. Every great discovery began with someone noticing that the data didn't quite fit the accepted explanation. The anomalies and tensions in our current observations might be nothing more than measurement errors or incomplete understanding. Or they might be the first hints of something profound, evidence that the universe is more complex, more dynamic, more alive than we've imagined. Deep within your brain, as you listen to these words, billions of neurons are firing in intricate patterns, creating your conscious experience of this moment. Each thought, each memory, each sensation emerges from electrochemical cascades that flow in one direction, from past to future, from cause to effect, from lower entropy to higher entropy. Your ability to remember yesterday but not tomorrow, to influence the future but not the past, to experience time as a flowing river rather than a static landscape, all of this seems to depend on entropy's relentless increase. And yet, in our thought experiment of a universe that reverses its age every billion years, entropy itself must somehow reverse. What would this mean for memory, for consciousness, for the very experience of being alive in such a cosmos? This question takes us into some of the deepest mysteries in physics and philosophy. The relationship between entropy, time, and consciousness touches on fundamental questions about the nature of reality, the emergence of complexity, and our place in the cosmic order. Tonight, as you rest in the quiet darkness, we're going to explore these mysteries gently, contemplating what it might mean to exist in a universe where entropy can flow backward, where time's river can reverse its course, where memory itself might work differently than we assume. Let's begin with entropy itself, this concept that seems so abstract yet governs so much of our experience. Entropy, in its simplest definition, is a measure of disorder or randomness in a system. A neat room has low entropy. A messy room has high entropy. An ice cube has low entropy. The same amount of water spread throughout a glass has higher entropy. A fresh battery has low entropy. A dead battery has high entropy. In each case, the second law of thermodynamics tells us that isolated systems naturally evolve from low entropy to high entropy, from order to disorder, from concentrated to dispersed. But entropy is more than just messiness. It's fundamentally about information and probability. A system has low entropy when it's in an unlikely special configuration. It has high entropy when it's in a likely generic configuration. Think about a deck of cards. There's only one way for the deck to be perfectly sorted by suit and rank. This is a low entropy state. But there are billions upon billions of ways for the deck to be shuffled randomly. These are high entropy states. If you shuffle a sorted deck, it will almost certainly become disordered. If you shuffle a random deck, it will almost certainly stay random. This is why entropy increases. There are vastly more high entropy states than low entropy states, so systems naturally evolve toward the more numerous possibilities. Your brain is an extraordinary entropy managing device. It maintains itself in an extremely low entropy state, with precisely organized neural structures, carefully regulated chemical concentrations, and intricate patterns of electrical activity. It does this by consuming energy from food, using that energy to pump entropy out into the environment. You breathe in oxygen and breathe out carbon dioxide. You consume complex organic molecules and excrete simpler waste products. You take in information from your environment and radiate heat. All of these processes increase the total entropy of the universe, while allowing your brain to maintain its remarkable organization. Memory formation is itself an entropy-increasing process. When you form a new memory, your brain physically changes. Synapses strengthen or weaken. New proteins are synthesized, neural pathways are reinforced. Each of these changes requires energy and increases the universe's total entropy. The memory itself is a kind of fossil, a record of a lower entropy state that has been preserved at the cost of increasing entropy elsewhere. You can remember the past because the past had lower entropy than the present, leaving traces, fossils, records that we call memories. But what would happen to memory in a universe where entropy could decrease? This is where our thought experiment becomes truly mind-bending. If entropy decreased globally, would memories run in reverse? Would you forget things you once knew and remember things that haven't happened yet? Would your consciousness flow backward through time, experiencing effect before cause, answer before question, death before birth? The answer might be more subtle and strange than simple reversal. Consider that your consciousness, your sense of self, your experience of time flowing from past to future, all emerge from the physical processes in your brain. These processes follow the laws of thermodynamics. They're oriented by entropy's increase. If entropy's direction reversed, the physical processes in your brain would reverse too. But, and this is the crucial point, your subjective experience might not change at all. Think about it this way. You experience time flowing from past to future because that's the direction in which you form memories, in which you process information, in which your thoughts unfold. If all of these processes reversed, you would form memories in the opposite direction, process information backward, think in reverse. But from your subjective perspective, you would still experience forming memories of what you call the past and anticipating what you call the future. It's just that what counts as past and future would have flipped relative to an external observer who somehow stood outside the reversal. This is profoundly counterintuitive, so let's explore it with an analogy. Imagine you're reading a book from beginning to end. You experience the story unfolding, characters developing, plot advancing. Now imagine someone else reads the same book from end to beginning. They experience a different story, characters undeveloping, plot retreating, events unhappening. But each reader has a coherent experience of reading, of following a narrative, of moving through the text in what feels like the forward direction to them. Similarly, consciousness in a time-reversed universe might experience its own version of forward, its own arrow of time, even though that arrow points in the opposite direction from ours. The beings in that reversed phase wouldn't experience remembering the future and forgetting the past. They would experience what they call remembering the past and anticipating the future. It's just that their past is our future, and their future is our past. This raises profound questions about the nature of consciousness and its relationship to physical processes. Is consciousness somehow independent of entropy's direction, able to experience its own temporal flow regardless of how physical processes unfold? Or is consciousness so tightly bound to entropy that it can only exist when entropy increases, meaning that conscious beings in a reversed universe would be fundamentally different from us, perhaps unrecognizably so? Some physicists and philosophers have suggested that consciousness might actually play a role in determining entropy's direction. The argument goes like this. Consciousness requires information processing. Information processing requires entropy increase. Therefore, consciousness can only exist in regions of space-time where entropy is increasing. In this view, the arrow of time isn't fundamental but emerges from the requirements of consciousness. We experience time flowing from past to future because that's the only direction in which consciousness is possible. But this leads to a kind of cosmic solipsism. If consciousness determines time's arrow rather than the other way around, then the universe's temporal direction might be different in different places, depending on where conscious observers exist. There might be regions where time flows forward, regions where it flows backward, and regions where it doesn't flow at all. The universe becomes a patchwork of temporal domains, each with its own arrow, determined by local conditions and the presence or absence of observers. In our thought experiment of a universe that reverses every billion years, consciousness might bridge the reversal in unexpected ways. As the universe approaches the reversal point, as entropy slows its increase and prepares to decrease, consciousness might experience strange phenomena. Time might seem to slow down or become fuzzy. Cause and effect might become ambiguous, memory might become unreliable, with past and future bleeding into each other. Or perhaps consciousness would simply cease during the reversal, like a computer rebooting. The universe would go through its reversal unconsciously, and consciousness would re-emerge on the other side, oriented to the new temporal direction, with no memory or awareness of the transition. From the perspective of conscious beings, time would always flow forward, always from past to future, even though the objective direction reverses periodically. There's another possibility, even stranger. Consciousness might be continuous through the reversal, but experience it as normal forward time. The reversal would be invisible from the inside, detectable only by hypothetical observers who could somehow stand outside time and watch the universe's evolution from a temporal distance. This would mean that what we call the past and future are just labels we attach to different temporal directions, not fundamental features of reality. The concept of memory becomes particularly fascinating in this context. In our normal experience, memories are records of past events, physical traces in our brains that preserve information about things that have already happened. We can't remember the future because the future hasn't happened yet, hasn't left any traces, hasn't created any records. But in a time-reversed universe, or during a reversal phase, this relationship would be inverted. Imagine a being living during a reversal phase. From our perspective, they would be losing memories of what we call their past and gaining memories of what we call their future. But from their perspective, they would be normally remembering their past, our future, and anticipating their future, our past. Their brains would be physically evolving backward from our perspective, but experiencing forward evolution from theirs. This might seem to create paradoxes. If someone in a reversed phase remembers our future, couldn't they send us information about what's going to happen? Couldn't this violate causality, create grandfather paradoxes, allow for closed time-like curves? The answer might be that communication between normal and reversed phases is impossible. The reversal might create a kind of temporal barrier, preventing any information from crossing between phases. Or perhaps the paradoxes resolve themselves through what physicists call Novikov self-consistency principle. This principle suggests that the universe arranges itself to prevent paradoxes. Any information that crosses between phases would be exactly the information that was always going to cross, creating consistent loops rather than paradoxes. The universe becomes a kind of four-dimensional crystal, with everything that happens, forward or backward, already embedded in its structure. Let's consider how entropy reversal might work on different scales. On the cosmic scale, entropy decrease might manifest as the universe becoming more organized, more structured. Dispersed gas would gather into clouds, diffuse radiation would concentrate into stars, the cosmic web would tighten and become more defined. This large-scale organization would happen slowly over millions of years, invisible to short-lived observers. On the galactic scale, dead stars might reignite, using the energy from the universe's contraction to restart fusion processes. Black holes might shrink, emitting matter and energy rather than absorbing it. Galaxies might become more organized, their spiral arms tightening, their stellar populations growing younger. These processes would take millions to billions of years, far longer than any civilization could observe. On the planetary scale, things become more complex. Planets are relatively isolated systems, not strongly coupled to cosmic expansion or contraction. Would Earth's entropy reverse during a cosmic reversal phase? Would erosion run backward, building mountains from sediment? Would the atmosphere become more pristine, pollution undoing itself? Would evolution run in reverse, complex organisms simplifying back toward bacteria? The answer might depend on how strongly planetary processes are coupled to cosmic ones. If the coupling is weak, planets might continue evolving normally even during cosmic reversal, islands of forward time in a backward universe. If the coupling is strong, planetary evolution might reverse too, but on timescales so long that life wouldn't notice. A reversal phase lasting 1 billion years might only undo a few million years of planetary evolution, barely noticeable in geological terms. On the biological scale, the situation becomes even more intriguing. Life is essentially an entropy managing system, creating local order at the expense of increasing universal disorder. Living things maintain themselves in low entropy states by consuming energy and excreting waste, by taking in organized matter and releasing disorganized heat. Would life be possible in a universe where entropy decreases? One possibility is that life would simply reverse its thermodynamic processes. Instead of consuming food and excreting waste, organisms might absorb waste and produce food. Instead of breathing in oxygen and breathing out carbon dioxide, they might do the reverse. Instead of growing from seed to maturity, they might shrink from maturity to seed. But from the organism's perspective, if such a perspective existed, everything might feel normal. Eating still feels like eating, breathing still feels like breathing, growth still feels like growth. Another possibility is that life as we know it would be impossible during reversal phases, replaced by something entirely different. Call it anti-life or reverse life. This wouldn't be life made of antimatter, but life whose thermodynamic processes run backward from our perspective. Such life might be unrecognizable to us, perhaps invisible, perhaps appearing as a kind of gradual organization of matter that we wouldn't identify as biological. The question of consciousness in a reversing universe touches on the hard problem of consciousness. How subjective experience emerges from objective physical processes. If consciousness is purely physical, emerging from neural activity, then it should reverse when entropy reverses. But if consciousness has some non-physical aspect, as some philosophers argue, it might maintain its own temporal direction independent of entropy. There's a thought experiment in philosophy called the experience machine that's relevant here. Imagine a machine that could give you any experience you want. You could experience being a great artist, a successful athlete, a beloved leader. Would you plug into such a machine? Most people say no, suggesting that we value not just experiences but real achievement, real connection, real existence. Similarly, in a reversing universe, we might ask whether reversed consciousness would be real consciousness, or just the appearance of consciousness running backward. The relationship between entropy and information is crucial to understanding consciousness in a reversing universe. Information theory tells us that information and entropy are intimately related. Processing information requires increasing entropy. Every computation, every thought, every decision increases the universe's total entropy. In a reversed universe, would information processing run backward? Would computations uncompute? Would decisions be unmade? This connects to the concept of computational irreversibility. Many computations are easy to perform in one direction, but practically impossible to reverse. It's easy to multiply two large prime numbers, but extremely difficult to factor their product. It's easy to scramble an egg, but impossible to unscramble it. It's easy to burn a book, but impossible to unburn it and recover the information. These irreversible processes are what give time its direction in our experience. But in a universe where entropy decreases globally, these irreversible processes might become reversible. The scrambled egg might unscramble. The burned book might unburn. The multiplied primes might spontaneously factor. This wouldn't violate any laws of physics. It would just require an incredibly unlikely coordination of microscopic events, the kind of coordination that might occur naturally in a universe where entropy is decreasing. Consider what this means for the nature of knowledge and learning. In our forward time universe, we learn by acquiring information, by building mental models, by accumulating experience. Our knowledge grows over time, ideally becoming richer and more complex. In a reversed universe, would knowledge shrink? Would learning become unlearning? Would wisdom transform into ignorance? Again, the answer might be a matter of perspective. Beings in a reversed universe might experience what they call learning, which from our perspective looks like forgetting. They might feel their knowledge growing even as from our perspective it shrinks. The subjective experience of learning might be independent of whether information is being accumulated or dissipated, depending only on the direction of the being's temporal experience. This brings us to the question of free will in a reversing universe. Our sense of free will, our feeling that we can influence the future but not the past, seems tied to entropy's increase. We can choose to break an egg but not to unbreak it. We can choose to speak words but not to unspeak them. We can choose to take actions that increase entropy but not actions that decrease it. In a reversed universe, would free will operate in reverse? Would beings feel they could influence what we call the past but not what we call the future? The question of free will is controversial even in our normal forward time universe. Some argue that free will is an illusion, that our choices are determined by prior causes stretching back to the Big Bang. Others argue that quantum indeterminacy or emergent complexity creates genuine freedom. In a reversing universe, these debates would take on new dimensions. determinism might run backward. Quantum indeterminacy might become quantum determinacy. The whole concept of choice might need to be reconsidered. As you lie there in the darkness, perhaps feeling your mind gently stretching to accommodate these strange ideas, consider that your own consciousness, your own experience of this moment, is itself a kind of miracle. The fact that atoms can arrange themselves into patterns that experience, that remember, that wonder about their own existence is perhaps the deepest mystery in the universe. Whether time flows forward or backward, whether entropy increases or decreases, the emergence of consciousness remains astonishing. In our billion-year reversal scenario, consciousness might be the thread that connects different phases, the constant that remains even as time's direction flips. Perhaps consciousness is not bound by entropy's arrow, but creates its own arrow, its own direction, its own meaning. Perhaps the universe reverses its age periodically, not despite consciousness, but because of it, creating cycles of experience, cycles of awareness, cycles of cosmic self-discovery. The possibility that memory and consciousness might work differently than we assume opens up profound questions about identity and continuity. If your memories could run backward, if your thoughts could flow in reverse, would you still be you? Is identity tied to the specific direction of our temporal experience, or is it something deeper, something that would persist even if time itself reversed? These questions might seem abstract, but they touch on fundamental issues about what it means to be human, to be conscious, to exist in time. Every moment of your life, every thought, every feeling, every memory is shaped by the fact that entropy increases, that time flows forward, that causes precede effects. If these fundamental facts could change, if they do change on cosmic scales, then our entire understanding of existence might need to be reconsidered. As we prepare to explore how Earth and life might fare in a reversing universe, take a moment to appreciate the extraordinary nature of your own consciousness. Your entropy made aware of itself, time experiencing itself, the universe looking at itself through your eyes. Whether time flows forward or backward, whether entropy increases or decreases, this moment of awareness, this gentle wandering in the darkness, is real and precious and irreplaceable. Here on Earth, as you lie listening to these words, our planet continues its ancient rhythms, seemingly oblivious to the vast cosmic drama we've been contemplating. The Earth spins on its axis once every 24 hours, creating the cycle of day and night that has governed life since its beginning. It orbits the sun once every year, carrying us through the seasons that shape our agriculture, our cultures, our very sense of time passing. These cycles feel permanent, unchanging, as reliable as anything in our experience. But what would happen to our small world if the universe itself began to reverse its age? Would Earth's story run backward too, or would our planet somehow remain an island of forward time in a reversing cosmos? To explore this question, we need to zoom in from the cosmic scales we've been contemplating to the more familiar scale of our home planet. Earth is about 4.5 billion years old, formed from the dust and gas left over from the sun's formation. For its first few hundred million years, it was a hellish place, bombarded by asteroids covered in magma, with a toxic atmosphere of methane, ammonia, and other gases we couldn't breathe. Gradually, over millions of years, the planet cooled. Water condensed from the atmosphere, forming the first oceans. The bombardment slowed, chemistry became more complex, and somewhere in those ancient seas, perhaps around hot volcanic vents, perhaps in warm tidal pools, perhaps in clay deposits, the first self-replicating molecules appeared. Life had begun. The story of life on Earth is a story of increasing complexity against the backdrop of increasing entropy. From simple self-replicating molecules came the first cells. From single cells came multicellular organisms. From simple multicellular forms came the incredible diversity we see today. Millions of species, from bacteria to blue whales, from mushrooms to giant sequoias, from insects to humans. Each increase in complexity required energy, organization, information processing. Life became increasingly sophisticated at managing entropy, creating local pockets of order in an increasingly disordered universe. But life's story hasn't been one of smooth progress. There have been at least 5 major mass extinctions, times when most species on Earth died out. The Permian extinction 250 million years ago killed 90% of marine species. The asteroid impact 66 million years ago ended the age of dinosaurs. After each extinction, life recovered, but it took millions of years, and the new ecosystem were different from what came before. Life is resilient but not invulnerable, creative but not predictable. Now imagine Earth existing in a universe that reverses its age every billion years. The reversal wouldn't happen suddenly. It would be a gradual process taking millions of years. At first, the changes would be so subtle as to be unnoticeable. Perhaps certain radioactive decay rates would shift slightly. Perhaps the cosmic ray flux would change. Perhaps the sun's energy output would vary in unexpected ways. These changes would be tiny, hidden within the natural variability of Earth's systems, but they would be the first signs of the approaching reversal. As the reversal progressed, more noticeable changes might occur. The sun, beginning its own reversed evolution, might start to grow slightly cooler and smaller rather than hotter and larger. This wouldn't be dramatic. The sun's evolution is so slow that even 1,000,000 years of reversal would barely affect it. But over tens of millions of years, the changes would accumulate. The sun might return to the temperature and luminosity it had millions of years earlier, affecting Earth's climate in complex ways. Earth's geology might also respond to the reversal, though exactly how is difficult to imagine. In our normal forward-time universe, the planet's interior is slowly cooling. Radioactive elements decay, releasing heat that drives plate tectonics, volcanism, and the magnetic field that protects us from cosmic radiation. In a reversed universe, would radioactive elements undecay, absorbing energy rather than releasing it? Would the planet's interior heat up rather than cool down? Would plate tectonics run in reverse, with ocean basins closing and reopening in opposite order? These geological changes would be incredibly slow, essentially unnoticeable on human timescales. Mountains that normally erode might instead grow slightly. Rivers that normally carve canyons might deposit sediment instead. Continents that normally drift apart might drift together. But these changes would take millions of years, far longer than human civilization has existed. To us, Earth would seem as stable and unchanging as ever. The more interesting question is what would happen to life during a reversal phase. Life depends on the flow of energy from low entropy to high entropy. Plants capture sunlight and use it to build complex molecules from simple ones. Animals eat plants or other animals, breaking down complex molecules to release energy. Decomposers break down dead organisms, returning nutrients to the ecosystem. This flow of energy and matter through ecosystems is fundamentally tied to entropy's increase. In a reversing universe, would these ecological processes reverse? Would decomposers assemble dead organisms from nutrients? Would animals produce plants rather than consume them? Would plants release sunlight rather than absorb it? This seems absurd, impossible, a violation of everything we understand about biology. And yet, if entropy can reverse on cosmic scales, why not on biological scales? One possibility is that life would simply die out during reversal phases, unable to function when entropy decreases. Earth would become sterile, waiting billions of years for the next forward phase when life could emerge again. But this seems unlikely. Life is incredibly adaptable, having survived ice ages, asteroid impacts, volcanic catastrophes, and dramatic atmospheric changes. It's hard to imagine that life couldn't find some way to persist through a reversal. Another possibility is that life would adapt to the reversal, evolving new metabolic processes that work with decreasing entropy rather than against it. Instead of breaking down food to release energy, organisms might absorb ambient energy to synthesize food. Instead of growing from birth to death, they might shrink from death to birth. Instead of evolving from simple to complex, they might evolve from complex to simple. This reverse life would be utterly alien to us, perhaps unrecognizable as life at all. But there's a third possibility, perhaps the most intriguing. Life might be buffered from cosmic reversals, continuing to evolve normally even as the universe around it reverses. Earth's biosphere might be like a bubble of forward time in a backward universe, maintaining its own arrow of time through the sheer complexity and momentum of its biological processes. Life has, after all, maintained itself through dramatic changes in Earth's environment. Perhaps it could maintain itself through changes in time's direction itself. This buffering might work through what physicists call decoherence. Quantum systems can exist in superpositions of states, including perhaps superpositions of different temporal directions. But interaction with the environment causes decoherence, forcing systems to choose definite states. Life, with its constant chemical reactions, its continuous information processing, its ceaseless activity, might create such strong decoherence that it maintains a consistent temporal direction regardless of what the universe does on larger scales. Think about what this means for evolution. In our forward time universe, evolution proceeds through variation and selection. Random mutations create variation. Natural selection favors variants that reproduce more successfully. Over time, this process creates increasingly complex and well-adapted organisms. It's a ratchet that moves primarily in one direction, toward greater fitness, greater complexity, greater information content. In a reversed universe, would evolution run backward? Would complex organisms gradually simplify? Would well-adapted species become less adapted? Would the tree of life converge rather than diverge, with diverse species merging back into common ancestors? This seems to violate the randomness that drives evolution. Mutations are random. They don't know which direction to go to reverse evolution's path. Perhaps during reversal phases, evolution would proceed differently, but not necessarily backward. Maybe mutations would still be random, but selection pressures would change. Maybe organisms would evolve to cope with decreasing entropy rather than increasing it. Maybe new forms of life would emerge, adapted to the strange conditions of a reversing universe. The tree of life might not converge but branch in entirely new directions, exploring possibilities that are forbidden in forward time. Consider human civilization in such a universe. Humans have existed for only about 300,000 years, civilization for only about 10,000 years, industrial technology for only about 200 years. These are eye blinks compared to the billion-year cycles we're contemplating. If a reversal happened tomorrow, beginning a process that would take millions of years to complete, would we even notice? At first, probably not. The changes would be far too subtle, far too slow. Scientists might notice tiny anomalies, particle physics experiments giving slightly unexpected results, astronomical observations showing minute discrepancies, geological processes behaving oddly. But these would be dismissed as experimental error or explained by refining our theories. It might take centuries or millennia of observations before the pattern became clear. By the time humanity realized that the universe was reversing, we might have evolved or transformed into something unrecognizable. In a few thousand years, at our current rate of technological development, we might merge with our machines, upload our consciousness to computers, spread throughout the solar system or beyond. The biological humans of today might be as distant from future humanity as we are from bacteria. These post-human beings might be better equipped to understand and perhaps even survive a temporal reversal. Or perhaps consciousness itself would protect us from the reversal. If consciousness creates its own arrow of time, as some theories suggest, then conscious beings might maintain their forward temporal direction even in a reversing universe. We would continue to remember the past and anticipate the future, to cause effects rather than be caused by them, to experience time flowing forward even as the universe around us flowed backward. We would be temporal islands, isolated from the reversal by the very nature of our awareness. The Earth's climate system presents interesting questions in a reversing universe. Our climate is driven by energy from the sun, modified by greenhouse gases, ocean currents, ice coverage, and countless feedback loops. It's a chaotic system, sensitive to small changes, capable of dramatic shifts between different stable states. Ice ages come and go. Ocean currents start and stop. Atmospheric composition changes. All of these processes are fundamentally thermodynamic, driven by entropy increase. In a reversing universe, would ice ages unhappen? Would glaciers flow uphill, gathering snow from the valleys and depositing it on mountain tops? Would ocean currents reverse, carrying heat from the poles to the equator rather than vice versa? Would carbon dioxide spontaneously separate from the atmosphere and return to fossil fuel deposits underground? These processes seem impossible, but they would be necessary if Earth's climate system truly reversed. More likely, the climate would find new equilibrium states appropriate to a reversing universe. The same physical processes, radiation, convection, evaporation, precipitation, would continue, but organized differently. Perhaps the climate would become more stable rather than less, with weather patterns converging rather than diverging, storms dissipating rather than forming, or perhaps entirely new climate phenomena would emerge, things that are impossible in forward time but natural in reverse time. The oceans, covering 71% of Earth's surface, would be particularly interesting during a reversal. Ocean currents are driven by temperature and salinity differences, wind patterns, and Earth's rotation. They transport heat from equator to poles, influence weather patterns, and support marine ecosystems. In forward time, these currents gradually mix ocean waters, distributing heat, nutrients, and dissolved gases. In reverse time, would the oceans unmix with distinct water masses separating rather than blending? Marine ecosystems might respond to reversal in unexpected ways. The ocean food web, from microscopic plankton to great whales, depends on the flow of energy and nutrients through the system. If this flow reversed, would predators become prey? Would food chains run backward? Would dead organisms reassemble from dissolved nutrients? Or would marine life find new ways to organize itself, new food webs that work with decreasing entropy rather than against it? The deep ocean, one of Earth's last frontiers, might harbor clues about how life could persist through reversals. Deep-sea organisms live in extreme conditions, crushing pressure, near freezing temperature, complete darkness. They've evolved remarkable adaptations, from bioluminescence to chemosynthesis to extreme longevity. Some deep-sea clams live for centuries. Some bacteria in ocean sediments may be millions of years old, barely metabolizing, barely alive. These organisms exist at the edge of life, in conditions that might resemble a reversing universe. Consider Earth's magnetic field, generated by convection in the liquid iron outer core. This field protects us from cosmic radiation and solar wind, making Earth's surface habitable. The field occasionally reverses, with north and south poles switching places. These reversals happen irregularly, sometimes after millions of years, sometimes after just thousands. During a reversal, the field weakens and becomes chaotic before reorganizing in the opposite direction. If the universe's temporal direction reversed, would Earth's magnetic field respond? Would past reversals unhappen, with the field strengthening and stabilizing rather than weakening and flipping? Or would the field continue its normal behavior, insulated from cosmic reversal by the complexity of core convection? The magnetic field might be a kind of temporal compass, indicating the local direction of time regardless of what the universe does on larger scales. Earth's interaction with space would change in interesting ways during a reversal. Currently, Earth receives energy from the sun and cosmic rays from deep space, while radiating infrared energy back to space. The planet slowly loses atmospheric gases to space, while occasionally capturing small asteroids and cometary material. In a reversing universe, would these flows reverse? Would Earth radiate energy toward the sun and receive infrared from space? Would it gather atmospheric gases from space while ejecting asteroids? These reversed interactions seem absurd, but they might make sense in the context of a fully reversing universe. If the sun is growing younger, it might absorb energy rather than emit it. If space itself is contracting, it might be warmer than expanding space. The entire energy economy of the Earth-Sun space system might reverse, with energy flowing in opposite directions but still maintaining the delicate balance that keeps Earth habitable. The question of habitability is crucial. Earth exists in what astronomers call the habitable zone, the range of distances from the sun where liquid water can exist on a planet's surface. Too close and water boils away, too far and it freezes. But the habitable zone isn't static. It changes as the sun evolves. In forward time, the sun is gradually getting hotter, pushing the habitable zone outward. Eventually, in about 1 billion years, Earth will become too hot for liquid water. In a reversing universe, with the sun growing cooler and smaller, the habitable zone would move inward rather than outward. Earth might become cooler, potentially entering a permanent ice age. But this would happen over millions of years, giving life plenty of time to adapt. And if the reversal is periodic, lasting only 1 billion years before reversing again, Earth might oscillate between too hot and too cold, but spend most of its time in the comfortable middle. Life's resilience gives us hope that Earth would remain habitable through cosmic reversals. Life has survived in boiling hot springs and frozen Antarctic ice. It thrives in battery acid and toxic waste. It lives miles underground and high in the atmosphere. Wherever there's a source of energy and basic chemical ingredients, life finds a way. Even if the universe's temporal direction reversed, life would probably adapt, evolve, and continue. But what kind of life would it be? Would conscious beings like us evolve during reversal phases, or is consciousness tied to forward time? Would technological civilizations arise, or does technology require entropy increase? Would the reversed beings be aware of us, the forward time inhabitants of Earth? Could they access our ruins, read our records, learn about our civilization, or would the reversal erase all traces of forward time existence? These questions touch on deep issues about the nature of information and its preservation through time. In forward time, information can be preserved indefinitely if protected from entropy. Books can last centuries, stone carvings millennia, fossils millions of years. But in reverse time, would preserved information spontaneously erase itself? Would books unwrite themselves, carvings smooth out, fossils dissolve back into living organisms? Or would information be immune to reversal, creating a kind of temporal palimpsest with messages from both forward and backward phases? Imagine future archaeologists living during a reversal phase, discovering artifacts from our forward time civilization. To them, these artifacts would be problematic, seeming to violate the laws of physics as they understand them. They might develop elaborate theories to explain these anomalies, never suspecting that they're simply remnants from a time when the universe ran in the opposite direction. Our civilization would be their Atlantis, their lost world, their impossible mystery. Or perhaps the reversal would be more selective, affecting some systems but not others. Large-scale cosmic processes might reverse while small-scale terrestrial processes continue normally. Earth might be like a clock that keeps ticking forward even when the cosmic clock runs backward. Life and civilization might continue their forward evolution through multiple cosmic reversals, accumulating experience and knowledge across cycles. The carbon cycle, essential to life as we know it, would face interesting challenges in a reversing universe. Carbon moves through Earth's systems, from atmosphere to plants, through photosynthesis, from plants to animals through consumption, from organisms to soil through decomposition, from soil to atmosphere through respiration. This cycle has maintained Earth's climate and supported life for billions of years. In reverse time, would carbon flow backward through this cycle? Would decomposition become composition, with soil spontaneously generating dead organisms? Would respiration become absorption, with organisms pulling carbon dioxide from the air rather than releasing it? Would photosynthesis reverse, with plants releasing oxygen and absorbing carbon dioxide? The cycle might reverse completely, partially, or not at all, depending on how strongly biological processes are coupled to cosmic ones. Water, the foundation of all known life, presents its own puzzles. The water cycle, evaporation, condensation, precipitation, collection, is driven by solar energy and gravity. In a reversing universe with a cooling sun, would the water cycle slow, stop, or reverse? Would rain fall upward? Would rivers flow uphill? Would oceans evaporate from the bottom up? These images seem surreal, impossible, but they might be necessary consequences of a truly reversing universe. More likely, water would continue to behave normally on Earth, even during cosmic reversal. The laws of chemistry wouldn't change. Gravity would still pull things down. The sun, even if cooling slightly, would still provide energy. The water cycle might slow or shift, but probably wouldn't reverse. Earth's water would continue to support life, though perhaps different forms of life adapted to different conditions. As you lie there contemplating Earth's fate in a reversing universe, consider how remarkable our planet is. In all our observations of the cosmos, we've found no other place quite like Earth, no other world with liquid water oceans, oxygen atmosphere, and abundant life. Earth seems to exist in a perfect balance, neither too hot nor too cold, neither too large nor too small, neither too close to its star nor too far. This balance has been maintained for billions of years through dramatic changes in solar output, atmospheric composition, and cosmic environment. If Earth can maintain this balance through ice ages and warm periods, through asteroid impacts and volcanic catastrophes, through magnetic reversals and solar storms, perhaps it can maintain it through temporal reversals too. Our planet might be more robust than we imagine, able to preserve its habitability and its life through cosmic cycles we're only beginning to contemplate. The story of Earth in a reversing universe is ultimately a story of resilience and adaptation. Whatever the cosmos throws at it, expansion or contraction, forward time or backward, increasing entropy or decreasing, Earth and its life would probably find a way to persist. We might not recognize the Earth of a reversal phase, with its backward rivers and uneroding mountains, its reverse ecosystems and temporal islands. But it would still be Earth, still be home, still be the small blue marble where consciousness emerged to contemplate its own existence. Now, as you lie there in the quiet darkness, I want to invite you on a journey unlike any we've taken before. Close your eyes if they aren't already closed, and let your breathing become slow and deep. Feel yourself sinking deeper into whatever surface supports you, becoming heavier, more relaxed, as if gravity itself is gently increasing its embrace. We're going to travel together through time, not the mere decades of a human lifetime, not even the millennia of human civilization, but through millions and billions of years. We're going to ride the cosmic tide through one complete reversal, experiencing what it might be like to live through the universe changing its temporal direction. Imagine yourself floating in space, far from any star or planet, surrounded by the vast darkness punctuated by distant points of light. You're not in a spaceship or a spacesuit. In this journey, you exist as pure consciousness, aware but not physical, able to observe without being affected by what you observe. You can see in all directions at once, perceive all wavelengths of light, sense the subtle currents of gravity and space-time. You are a witness to the cosmos, floating in the void, watching the universe evolve around you. The year, if years have meaning here, is somewhere in the distant future. The universe has been expanding for perhaps 20 billion years, far longer than its current age. The galaxies around you are farther apart than they are in our time. The cosmic web has stretched and thinned. Stars are older, redder, dimmer. Many galaxies have exhausted their gas supplies and no longer form new stars. The universe is middle-aged, perhaps beginning to feel its age, settling into what seems like a long, slow decline toward heat death. But you, with your cosmic awareness, can sense something subtle beginning to change. The expansion of space, which has been accelerating for billions of years, is starting to slow. Not dramatically, not suddenly, but gradually, gently, like a thrown ball reaching the peak of its arc. The dark energy that has been pushing space apart is weakening, transforming, perhaps preparing to reverse its effect. You can feel it in the way distant galaxies move, in the temperature of the cosmic microwave background, in the quantum fluctuations of empty space itself. Watch now as millions of years pass like seconds. See how the expansion continues to slow. Galaxies that were racing apart begin to coast. The cosmic web, which had been stretching like taffy, begins to hold its shape. The universe reaches a moment of perfect balance, neither expanding nor contracting, holding its breath at the turning point of the cosmic tide. This is the moment of reversal, though it's not a moment but an era, lasting perhaps millions of years, as the universe prepares to change direction. And then, so slowly that it would be imperceptible to any observer with a human lifespan, the universe begins to contract. Space itself starts to shrink, carrying galaxies along with it. Not falling together through space like objects dropped, but moving together because space between them is diminishing. The cosmic web begins to tighten, voids begin to shrink. The large-scale structure of the universe starts to become more compact, more organized, more defined. Feel yourself drifting with this cosmic current, carried along by the contraction of space. You're not moving through space. Space itself is moving, flowing, carrying you like a leaf on a river. The sensation is peaceful, gentle, inevitable. There's no violence in this reversal, no catastrophic collapse. Just the slow, patient turning of the cosmic tide, as natural as breathing, as gentle as sleep. As millions more years pass, you begin to notice changes in the galaxies around you. They're not just moving closer together, they're changing in character. Old, red, dead galaxies are beginning to show signs of new activity. Not new in the sense of moving forward, but new in the sense of reversing their aging. Stars that had long ago exhausted their fuel are beginning to brighten. Their spectra are shifting from red toward yellow, from yellow toward white, from white toward blue. They're growing younger. Focus on one galaxy, a spiral like our Milky Way but older. Its spiral arms diffuse, its star formation long ceased. Watch as the reversal progresses. The spiral arms begin to tighten, to become more defined. Gas that had been dispersed throughout the galaxy begins to collect into clouds. Dead stellar remnants, white dwarfs, neutron stars, black holes, begin to show activity. The white dwarfs warm and expand. The neutron stars decompress. The black holes, mysteriously, begin to shrink, emitting matter and energy rather than absorbing it. This is not resurrection in any spiritual sense, but a physical reversal of stellar evolution. The galaxy is not remembering its past and returning to it, but evolving backward through the same stages it once evolved forward. It's like watching a flower bloom in reverse, petals folding back into the bud shrinking back into the stem. Beautiful, strange, but following its own logic, its own physics, its own necessity. Now expand your awareness to encompass millions of galaxies, billions of stars. Everywhere the same process is occurring. The universe is growing younger, not returning to youth, but growing toward it, evolving backward through time. Entropy, which had been increasing for billions of years, is now decreasing. Order is emerging from chaos. Structure is forming from randomness. The arrow of time has reversed and the universe is flowing backward along the temporal stream. But notice something important. From your perspective as a conscious observer, you still experience time flowing forward. You remember what you've observed. You anticipate what you'll observe next. Your thoughts flow from premise to conclusion, from question to answer. Even though the universe around you is reversing, your subjective experience of time continues in the direction you've always known. You're an island of forward time in an ocean of backward time, maintaining your own temporal direction through the mere act of observation. As billions of years pass in your accelerated perception, the universe continues to contract and grow younger. Galaxies move closer together, some beginning to merge in reverse, not colliding and combining, but carefully separating, like dancers moving apart in perfect synchronization. The cosmic microwave background, which had cooled to near absolute zero, begins to warm. The universe is returning to a younger, hotter, denser state. But slowly, patiently, without violence or catastrophe. Watch as the first stars, or are they the last stars, begin to form in reverse, not collapsing from gas clouds, but emerging from them, as if the gas knows exactly what shape to take, what density to achieve, what temperature to reach. These are not random events, but precisely orchestrated reversals of previous events. Every star that unforms in this reversed universe once formed in the forward universe. Every pattern that emerges existed before. The universe is not creating but uncreating, not composing but decomposing, yet doing so with a kind of cosmic memory that preserves information even as it reverses processes. The sensation of watching this is deeply peaceful, almost hypnotic. There's a rhythm to it, a pulse, like watching waves retreat from a beach, each one following the same path it took coming in but in reverse. Your breathing naturally synchronizes with this cosmic rhythm. Inhale as 1,000,000 years pass. Exhale as another 1,000,000 years flow by. You are breathing with the universe, sharing its rhythm, participating in its reversal, even while maintaining your own forward direction through time. Now something remarkable happens. As the universe continues to contract and grow younger, you begin to see patterns you hadn't noticed before. The reversal is not uniform. Some regions reverse faster than others. Some galaxies maintain pockets of forward time even as the space around them flows backward. These are like eddies in the temporal stream, places where the reversal is incomplete or delayed. Perhaps these are regions where consciousness exists, where observers like yourself create bubbles of forward time through their observation. In one of these temporal eddies, you see something extraordinary, a planet that looks remarkably like Earth, orbiting a star that looks remarkably like our Sun. But this is not our Earth, not our Sun. This is another world, perhaps millions of light years away, perhaps billions of years in the future, or is it the past? In a reversing universe, the distinction becomes meaningless. This world is experiencing its own story, its own evolution, its own emergence of life and consciousness. Float closer to this world, drawn by curiosity. As you approach, you see that it's indeed alive, covered with clouds and oceans, continents and ice caps. But the life here is strange, alien, adapted to the reversing universe. You watch forests growing backward, from ancient trees to saplings to seeds. You see rivers flowing uphill, carrying sediment from the seas back to the mountains. You see animals living their lives in reverse, from death to birth, from age to youth. Yet from the perspective of the beings on this world, if conscious beings exist there, everything would seem normal. They would experience growing from birth to death, even if we would see them growing from death to birth. They would see rivers flowing downhill, even if we see them flowing uphill. They would remember their past and anticipate their future, even though their past is our future, and their future is our past. They are living their lives forward through time, even in a universe that we perceive as running backward. This is the paradox and the beauty of the reversal. Time's direction is not absolute but relative. Forward and backward are not universal truths but perspectives, ways of experiencing the flow of events. In a reversing universe, every conscious being might experience their own forward, their own arrow of time, even while the cosmos as a whole flows in the opposite direction. We are all temporal islands, maintaining our own subjective time while floating in the objective time of the universe. Continue drifting through this reversing universe, watching billions of years pass in moments. See how the cosmic web continues to tighten, how galaxies continue to grow younger, how the universe becomes increasingly organized and structured. You're approaching the minimum point of the cycle, the moment when the universe will be youngest, densest, hottest. Not a big bang, but a big bounce, a turning point where contraction will become expansion again. As you approach this turning point, the rate of change accelerates. Galaxies rush together. The cosmic microwave background heats up dramatically. Space itself becomes dense with energy. But still, there's no violence, no catastrophe. The universe knows how to reverse, has done it before, will do it again. This is not an ending, but a transformation. Not a death, but a rebirth. Not collapse, but a careful, orchestrated transition from one phase to another. At the moment of minimum size, though moment is the wrong word for a process that takes millions of years, something remarkable happens. The universe pauses, not frozen but balanced, like a pendulum at the end of its swing. All the matter and energy of the cosmos is compressed into a volume much smaller than today, but not infinitely small. The temperature is high, but not infinite. The density is extreme, but not singular. This is not the singularity of classical Big Bang theory, but something subtler, something that preserves information even through the reversal. And then, as gently as it began, the reversal reverses. The universe begins to expand again. Entropy begins to increase. Time's arrow flips back to its original direction. The cosmic tide has turned, and a new cycle has begun. But this is not simply a repeat of the previous cycle. The universe has memory. Patterns from the previous cycles are encoded in the quantum fluctuations of fields, in the distribution of matter and energy, in the subtle correlations that survive the bounce. Watch as the universe begins its new expansion phase. It looks similar to the Big Bang we theorize about, but it's not a beginning, it's a continuation. Particles form from energy. Forces separate and distinguish themselves. The first atoms come together. But these processes carry echoes of all the cycles that came before. The universe is not repeating, but evolving, learning, complexifying across cycles in ways we can barely imagine. As you float in this newly expanding universe, watching new galaxies form, or are they old galaxies reforming, you realize that you've witnessed something profound. The universe is not dying but cycling. It's not a one-way journey from birth to death, but an eternal dance, a cosmic breathing, an endless exploration of possibilities. Each cycle is similar but not identical. Each reversal preserves some information while transforming other information. The universe is not static but dynamically eternal, always changing yet always continuing. Feel yourself beginning to drift back toward your own time, your own place in the cosmic cycle. The journey through billions of years begins to slow. The cosmic perspective begins to narrow. You're returning to the human scale, the human time frame, the human experience of a universe that seems to flow steadily from past to future. But you carry with you the memory of what you've seen, the vast cycles, the gentle reversals, the eternal dance of expansion and contraction. As you settle back into your body, back into this moment, back into the darkness where you lie listening to these words, take a deep breath. Feel the air flowing into your lungs, entropy increasing as oxygen combines with carbon in your cells. Feel your heart beating, maintaining order through constant energy expenditure. Feel your consciousness experiencing this moment. creating its own arrow of time through the act of observation and memory. You are back in our familiar universe, where time flows forward, where entropy increases, where causes precede effects. But you've seen, or imagined, how it might be otherwise. You've experienced the possibility that our universe, with its apparent one-way journey from Big Bang to heat death, might be just one phase of something far grander, far more beautiful, far more eternal than we usually imagine. The journey you've just taken was imagination, not observation. We have no evidence that the universe actually reverses its age every billion years. We may never have such evidence. The cycles, if they exist, operate on scales that dwarf human experience, human history, even human evolution. We are mayflies contemplating seasons, unable to directly observe the patterns we're imagining. But the journey serves a purpose beyond literal truth. It expands our conception of what's possible. It loosens our assumptions about time, causality, and the nature of existence. It reminds us that the universe might be stranger, more wonderful, more alive than our current theories suggest, and it gives us a kind of cosmic perspective that can be deeply calming, deeply peaceful as we drift towards sleep. You've ridden the cosmic tide through expansion and contraction, through forward time and backward, through aging and reversal. You've seen, in imagination, if not in reality, how the universe might breathe, might pulse, might dance through eternal cycles. You've experienced yourself as both part of this cosmic process and somehow separate from it, maintaining your own temporal direction even as the universe reverses around you. This dual perspective, embedded in the universe yet observing it, subject to its laws yet somehow transcending them, is the gift of consciousness. We are the universe becoming aware of itself, questioning itself, imagining alternatives to itself. Whether time flows forward or backward, whether entropy increases or decreases, whether the cosmos expands forever or cycles eternally, this moment of awareness, this gentle wandering in the darkness, is real and precious.